quiet of night, beneath a blanket of stars, humanity has always looked up and wondered. This wondering, this curiosity, is woven into the fabric of who we are. Since our earliest days, we have been explorers, wanderers, seeking what lies beyond the next horizon. Think back to those first brave souls who pushed their wooden vessels into uncharted waters, guided only by stars and faith. They could not know what awaited them, yet they journeyed onward. From Polynesian navigators crossing vast Pacific expanses, to Vikings braving the North Atlantic, from Zheng, he commanding treasure fleets, to Columbus, sailing west toward an uncertain destiny, human history is written in voyages. We crossed oceans, we scaled mountains, we traversed deserts. Each boundary we encountered became not a wall, but a doorway to something new. And when we had mapped every continent, charted every coastline, and climbed every peak on Earth, our gaze naturally turned upward. The sky above us, that ever-present canopy of blue, giving way to the velvet darkness of night, beckoned us with its mysteries. What lay beyond our atmosphere? What secrets did those twinkling lights hold? Could we somehow reach them? In 1957, a small metal sphere called Sputnik 1 broke free from Earth, becoming our first emissary to space. Just 12 years later, human footprints pressed into lunar dust. We had left our home world. We had touched another world, and in doing so, we forever changed our perspective of what might be possible. Now we find ourselves at the beginning of what may be our greatest journey. The universe spreads before us, unimaginably vast. Hundreds of billions of galaxies, each containing hundreds of billions of stars, countless planets, untold possibilities. It calls to the explorer in our DNA. But space is not like our oceans or continents. The distances defy comprehension. The challenges seem insurmountable. The physics that govern travel between stars appear unforgiving. Yet, we dream. We calculate. We imagine. How far can we truly go? What are the limits that constrain us? Are they merely technological hurdles we might one day overcome? Or are they fundamental barriers set by the laws of physics themselves? Perhaps they are biological limitations of our fragile human forms. Or maybe they exist within our minds, in our ability to conceptualize time and distance beyond human scales. Tonight, we embark on a journey of possibilities. We will explore not just where humans have gone, but where we might go. We will contemplate technologies that exist today and those that remain theoretical. We will gaze toward nearby planets, distant stars, and galaxies unimaginably far away. As we drift through the cosmos together, consider this question gently in your mind. In our universe of 100 billion galaxies, how far might humanity reach? What corners of creation might someday know our touch? And what regions will forever remain beyond our grasp, known only through the light they send our way? Our story begins close to home, with the small steps we have already taken. For while our dreams may stretch to the ends of the universe, our physical presence remains tethered to the cosmic neighborhood of Earth. Let us start our journey with what we know, with what we have accomplished, before we reach for the stars. Rest your mind now as we float outward from our blue marble home, past the boundaries we have already crossed, and toward those that await us in the deep cosmic ocean of tomorrow. Our journey into space began not with a grand leap, but with cautious steps. The story of human spaceflight is young, barely spanning 7 decades in our species' long history. Yet in this brief time, we have accomplished what our ancestors could only dream about in myths and legends. We have left Earth. We have touched other worlds. We have cast our gaze across the cosmos and learned about our place within it. These achievements represent the opening chapter of humanity's cosmic story, a prelude to what may become our greatest adventure. Long before the first rocket broke free from Earth's gravity, humans dreamed of space travel. Ancient myths spoke of journeys to the heavens. Chinese folklore tells of Chang'e, who flew to the moon. Greek mythology described Icarus soaring toward the sun. By the late 19th century, visionaries like Jules Verne were imagining scientifically plausible methods of space travel in works such as From the Earth to the Moon. In the early 20th century, Russian schoolteacher Konstantin Tsiolkovsky developed the mathematical principles of rocketry, understanding that only rockets could function in the vacuum of space. The practical development of rockets powerful enough to reach space began with Robert Goddard in the United States and later continued in Germany under Wernher von Braun. These early pioneers faced skepticism and limited funding, yet they persisted in their belief that humanity could break free from Earth's gravitational bonds. World War II accelerated rocket development for military purposes, leading to the German V-2, the first ballistic missile. After the war, captured V-2 technology, and scientists became the foundation for both American and Soviet space programs. The first artificial satellite, Sputnik 1, launched by the Soviet Union on October 4, 1957, was modest in its capabilities. A polished metal sphere just 58 centimeters in diameter, carrying only basic radio transmitters that beeped a simple signal back to Earth. But this small object represented something profound. Humanity had placed an object into orbit around our planet. We had reached space. The cosmic ocean was no longer entirely beyond our grasp. The early space race that followed was driven by Cold War competition between superpowers, but it yielded remarkable achievements in rapid succession. In April 1961, Yuri Gagarin became the first human to orbit Earth, spending 108 minutes in space aboard Vostok 1. His flight proved humans could survive in the vacuum beyond our atmosphere. Just 3 weeks later, Alan Shepard became the first American in space with a brief suborbital flight. These initial missions were extraordinarily risky. Early spacecraft were cramped capsules with minimal systems, offering their occupants little more than the essentials needed to survive. The rockets beneath them were adapted from military ballistic missiles, machines designed for war repurposed for exploration. Reliability was far from guaranteed. These first astronauts and cosmonauts were test pilots pushing the boundaries of the possible, knowing each mission could end in disaster. Yet progress accelerated at an astonishing pace. By 1962, John Glenn orbited Earth 3 times. By 1965, cosmonaut Alexei Leonov conducted the first spacewalk, floating free outside his spacecraft for 12 minutes. And in 1969, just 12 years after Sputnik, Neil Armstrong and Edwin Buzz Aldrin walked on the surface of the Moon while Michael Collins orbited above. The Apollo moon landings represent the furthest humans have physically traveled from Earth. At an average distance of 384,400 kilometers, the Moon orbits just far enough that the entire Earth can be hidden behind a thumb held at arm's length. The lunar missions carried 24 different astronauts to lunar orbit, with 12 of them walking on another world. The journey took approximately 3 days each way, using the most powerful rocket ever built, the Saturn V. Consider this achievement in historical context. Just 66 years separated the Wright brothers' first powered flight at Kitty Hawk from Neil Armstrong's first footprint on lunar soil. In a single human lifetime, we went from barely leaving the ground to leaving our home world entirely. After the Apollo program ended in 1972, human spaceflight retreated to low Earth orbit, where it has remained ever since. The Soviet Union and later Russia built a series of space stations, culminating in Mir, which operated from 1986 to 2001. The United States launched Skylab, which hosted 3 crews between 1973 and 1974. These early stations were followed by the International Space Station, a collaborative project involving 5 space agencies and 15 countries. Construction began in 1998, and the station has been continuously occupied since November 2000. Orbiting at an altitude of approximately 400 kilometers, the ISS circles Earth every 90 minutes. More than 250 people from 19 countries have visited this outpost, conducting thousands of scientific experiments in the unique environment of microgravity. But while humans have remained close to Earth, our robotic emissaries have ventured much further. The Soviet Venera program sent probes to Venus, with Venera 7 achieving the first successful landing on another planet in 1970. The harsh conditions on Venus, with surface temperatures around 460 degrees Celsius and crushing atmospheric pressure 90 times that of Earth, meant these probes survived for only short periods, the longest lasting just over 2 hours. Mars has seen even more attention. Since the first successful flyby by Mariner 4 in 1965, we have sent orbiters, landers, and rovers to the Red Planet. The Curiosity and Perseverance rovers continue to explore the Martian surface today, seeking signs of ancient habitability and collecting samples that may one day be returned to Earth. The outer solar system has been explored by a series of increasingly sophisticated spacecraft. Pioneer 10 and 11, launched in the early 1970s, were the first to visit Jupiter and Saturn. They were followed by the more capable Voyager probes, which took advantage of a rare planetary alignment to conduct a grand tour of the outer planets. Voyager 1 flew past Jupiter in 1979 and Saturn in 1980. Its twin, Voyager 2, visited Jupiter, Saturn, Uranus, and Neptune, completing its planetary encounters in 1989. These missions revolutionized our understanding of the gas giants and their complex systems of moons, rings, and magnetic fields. Later missions have built upon this foundation. The Galileo spacecraft orbited Jupiter from 1995 to 2003, while Cassini spent 13 years studying Saturn from 2004 to 2017. New Horizons provided our first close look at Pluto during its 2015 flyby, revealing a surprisingly dynamic world with nitrogen ice plains and water ice mountains. Perhaps most remarkably, both Voyager spacecraft continue to operate more than 45 years after launch. In August 2012, Voyager 1 became the first human-made object to enter interstellar space, crossing the boundary where the Sun's influence gives way to the wider galaxy. Voyager 2 followed in November 2018. These venerable explorers are now more than 23 billion kilometers from Earth, so distant that their radio signals, traveling at the speed of light, take over 20 hours to reach us. The Voyagers carry golden records containing sounds and images of Earth, a message in a bottle cast into the cosmic ocean. They will continue their journey indefinitely, silent ambassadors from humanity that will outlast our civilization and possibly even our species. In about 40,000 years, Voyager 1 will pass within 1.6 light-years of the star, Gliese 445, the closest stellar encounter currently projected. Beyond these planetary missions, we have also deployed space telescopes that have revolutionized our view of the universe. The Hubble Space Telescope, launched in 1990, has observed galaxies forming shortly after the Big Bang. The James Webb Space Telescope, with its larger mirror optimized for infrared light, is now peering even deeper into cosmic history and examining the atmospheres of planets around other stars. We have placed spacecraft in special orbits to study the Sun from different angles. We have landed on asteroids and comets, even returning samples to Earth. We have mapped our home planet in unprecedented detail, tracking changes in its climate, forests, ice caps, and oceans. For all these accomplishments, however, the scope of human presence in space remains remarkably limited. Since Yuri Gagarin's historic flight, fewer than 600 people have reached orbit. The vast majority never ventured beyond a few hundred kilometers of altitude. Only 24 humans have traveled beyond low Earth orbit to reach the Moon, and none have done so since Apollo 17 in December 1972. Our most distant outpost, the International Space Station, orbits just 400 kilometers above Earth's surface. If Earth were scaled down to the size of a standard classroom globe, the ISS would orbit approximately 1 centimeter from its surface. On this same scale, the Moon would be nearly 10 meters away. Mars at its closest approach would be over 150 meters distant, and the nearest star would lie thousands of kilometers beyond. This perspective reveals how close to home we remain. For all our technological prowess, for all our exploratory spirit, humans have barely left Earth's immediate vicinity. We have taken our first steps into a vast cosmic ocean, but we remain very much at the shoreline. The reasons for these limitations are many, and they shape the possible futures of human space exploration. Rocket technology has improved incrementally since the Apollo era, but not fundamentally. The physics of chemical propulsion sets strict limits on what we can achieve. The challenges of keeping humans alive in the hostile environment of space for long durations remain substantial. The economics of spaceflight mean that every kilogram lifted from Earth's surface comes at significant cost. Yet there are signs of change. The emergence of commercial spaceflight companies has reduced launch costs and increased innovation. New propulsion technologies are under development. Plans for returning humans to the Moon and eventually sending them to Mars, are taking shape. As we look to the future and contemplate how far humans might travel beyond Earth, we must reckon with both the lessons of what we have already accomplished and the constraints that have thus far kept us close to home. The story of human spaceflight is still in its earliest chapters. Where it leads depends on how we address the fundamental challenges of venturing deeper into the cosmos. What we've achieved so far may seem modest when measured against the scale of the universe, or even our own solar system. The furthest humans have traveled from Earth is still less than 1.3 light seconds, an infinitesimal fraction of even the distance to our closest stellar neighbor. Our robotic explorers have reached the edge of interstellar space, but they have covered less than 0.02 of a light year in nearly half a century of travel. Yet these achievements represent the initial steps of a technological species beginning to explore beyond its home world. The Wright brothers' first flight traveled a mere 37 meters. Just 66 years later, Apollo astronauts traveled nearly 1 million times further. What distances might humans or their robotic emissaries reach in another century of development? What about a millennium? What are the ultimate limits to how far we might travel? To answer these questions, we must first understand the barriers that currently constrain us, the technological horizons that might overcome them, and the fundamental limits that physics may impose. Our journey beyond Earth has just begun, but already we can see both the challenges ahead and the tantalizing possibilities that beckon us onward. The question is not simply how far we have gone, but how far we might go. And to understand that, we must examine the limitations of our current technology and the physical realities that govern travel through the cosmic ocean. Let us reflect further on the significance of what we have achieved. Each milestone in space exploration has revealed new insights about our universe and ourselves. The first images of Earth from space showed us our planet as a fragile blue marble suspended in darkness, without visible borders or divisions, fundamentally changing how many people perceived our world. The Apollo missions brought back 382 kilograms of lunar rocks and soil, allowing scientists to develop new theories about the formation of the Earth-Moon system. The twin Voyager spacecraft revealed the complexity of the outer planets, discovering active volcanoes on Jupiter's moon Io, liquid hydrocarbon lakes on Saturn's moon Titan, and Neptune's great dark spot. Space exploration has yielded practical benefits as well. Communications satellites have connected the globe, enabling instant transmission of information across vast distances. Weather satellites save countless lives by providing early warning of dangerous storms. Earth observation satellites monitor crops, forests, ice caps, and pollution, giving us unprecedented knowledge about our changing planet. Navigation satellites guide ships, aircraft, and now everyday travelers with meter-level precision. These applications have become so woven into daily life that we often forget they depend on space technology. The International Space Station represents another kind of achievement. Beyond its scientific output, it demonstrates how former adversaries can cooperate on complex technological projects. With 15 participating nations, the ISS embodies international collaboration in pursuit of knowledge. Astronauts and cosmonauts from different countries live and work together in orbit, transcending the political divisions that often separate us on Earth. This diplomatic dimension of space exploration offers a model for addressing global challenges that require multinational solutions. Commercial spaceflight has emerged as a significant new chapter in space exploration. Companies like SpaceX, Blue Origin, and many others have developed new launch vehicles, spacecraft, and business models that are reducing the cost of access to space. Reusable rockets, once considered impractical, now routinely return to Earth for refurbishment and reflight. Small satellites, some no larger than a shoebox, are being deployed in constellations of hundreds or thousands, providing services from internet connectivity to high-frequency Earth observation. Tourism in space, long a dream, is becoming reality with suborbital flights and stays aboard private space stations on the horizon. Yet for all these accomplishments, we must acknowledge how limited our physical reach remains. If the solar system was scaled down so that the sun was the size of a grapefruit, Earth would be a pinhead about 15 meters away. On this scale, the Voyager probes, our most distant emissaries, would have traveled less than 200 meters from the grapefruit sun. The nearest star would be over 4,000 kilometers away. The vastness of space humbles even our greatest technological achievements. As we prepare to explore what might be possible in the future, we should carry with us both pride in what we have accomplished and humility about how far we have to go. The universe is unimaginably large, with distances that challenge our comprehension. Yet, in just 7 decades of spaceflight, we have learned more about our cosmic surroundings than in all previous human history combined. The path forward will not be easy. The challenges of propulsion, life support, radiation protection, and social organization for long-duration missions are substantial. Yet the history of space exploration teaches us that what seems impossible today may become achievable tomorrow. The Apollo program began when spaceflight was in its infancy, with only a handful of people having orbited Earth. 8 years later, humans walked on the Moon. What might we accomplish with sufficient will, resources, and ingenuity in the decades and centuries to come? As we turn our attention to future possibilities, remember that each step outward builds upon what came before. The spacecraft that might one day carry humans to Mars will incorporate lessons learned from the International Space Station. The probes that might explore the oceans of Europa will draw upon the heritage of the Voyager and Galileo missions. The telescopes that might detect biosignatures on distant exoplanets evolved from Hubble and James Webb. We stand today at the shoreline of the cosmic ocean, having waded in just far enough to sense its vastness. Our achievements in space exploration represent humanity's first tentative steps into this great unknown. The question before us now is how much further we might go, what boundaries we might cross, and what wonders we might discover as we venture deeper into the universe that surrounds us. As we contemplate journeys beyond our immediate cosmic neighborhood, we must first understand the technological constraints that currently bind us close to Earth. Our present limitations are not merely matters of engineering that time and innovation will inevitably overcome. Some represent fundamental challenges that arise from the physics of spaceflight itself, challenges that even future technologies may struggle to address. The distance scales of space travel are difficult for the human mind to truly comprehend. We evolved to understand distances we could walk in a day, not the millions and billions of kilometers that separate planets. Even the Moon, our closest celestial neighbor, orbits at a distance that would take a commercial jetliner over 2 weeks of continuous flight to reach. Mars, at its closest approach, is still about 150 times further away than the Moon. These vast distances mean that any technology we develop for space travel must be extraordinarily reliable, efficient, and capable of sustaining human life for unprecedented durations. When we launched the first artificial satellites and human beings into orbit, we were pushing the very limits of mid-20th century technology. The computer that guided Apollo missions had less processing power than a modern digital watch. The materials used in early spacecraft were often adapted from aircraft technology, rather than purpose-built for the unique environment of space. Today, we have far more advanced computers, materials, and engineering techniques, yet the fundamental physics of space travel remains unchanged. We have better tools to address the challenges, but the challenges themselves are just as formidable as they were at the dawn of the space age. Let us begin with the most basic problem of space travel: propulsion. Nearly all spacecraft launched to date have relied on chemical rockets, a technology whose principles have remained largely unchanged since the Chinese invented gunpowder over a millennium ago. While modern rockets are vastly more sophisticated than their predecessors, they still operate on the same fundamental principle of action and reaction described by Newton's third law of motion. A chemical rocket works by combining fuel and oxidizer to create a high-temperature, high-pressure gas that is expelled through a nozzle. The force of this expelled gas pushing in one direction propels the rocket in the opposite direction. This method is reliable and produces high thrust, allowing rockets to overcome Earth's gravity and accelerate spacecraft to orbital velocities exceeding 28,000 kilometers per hour. However, chemical rockets face a severe limitation in their efficiency, measured by a value called specific impulse. This value represents how much momentum can be obtained from a given amount of propellant. The theoretical maximum specific impulse for chemical rockets is constrained by the energy released in chemical reactions, and the most efficient chemical fuels, liquid hydrogen and liquid oxygen, approach this limit closely. Even with perfect engineering, we cannot extract more energy from these chemical bonds than physics allows. This limitation becomes especially problematic due to what rocket scientists call the tyranny of the rocket equation. Developed by Konstantin Tsiolkovsky in the early 20th century, this equation reveals a harsh reality. To accelerate a payload to a given velocity, a rocket must carry propellant, but this propellant adds mass that itself must be accelerated, requiring even more propellant, creating a compounding effect. The result is that for missions beyond Earth orbit, chemical rockets must be enormous relative to their payload. The Saturn V moon rocket stood 111 meters tall, weighed 2,800 metric tons at launch, yet delivered a command module and lunar lander with a combined mass of less than 50 metric tons to lunar orbit. More than 98% of the rocket's mass was propellant, structure, and engines that were discarded during the journey. This inefficiency places severe constraints on how far we can practically travel using chemical propulsion alone. A mission to Mars already represents a significant challenge, requiring careful planning of launch windows when Earth and Mars are favorably aligned, typically every 26 months. Using current technology, a one-way trip to Mars takes between 6 and 9 months, during which astronauts would be exposed to radiation, microgravity, and isolation in a confined spacecraft. Traveling to the outer planets using chemical propulsion would be even more challenging. Jupiter, at its closest approach to Earth, is still more than 600 million kilometers away, about 1,600 times the distance to the Moon. A direct flight using the most powerful rockets available would take years, requiring a spacecraft that could sustain human life for the entire journey without resupply from Earth. Beyond propulsion, protecting human life during extended space missions presents another set of interconnected challenges. The space environment is hostile to life as we know it. Outside Earth's protective magnetosphere and atmosphere, cosmic radiation and solar particles bombard spacecraft continuously. A journey to Mars would expose astronauts to radiation doses approaching or exceeding NASA's career lifetime limits for cancer risk. Longer journeys would compound this exposure. Current radiation shielding technology relies primarily on mass, placing materials like water, polyethylene, or aluminum between astronauts and the radiation environment. However, effective shielding requires substantial mass, creating a conflict with the rocket equation's demand for lightweight vehicles. Some radiation, particularly galactic cosmic rays, consisting of high-energy particles, can penetrate even thick shielding or create secondary radiation when striking shield materials. The microgravity environment of space presents another health challenge. Without the constant pull of Earth's gravity, human bodies begin to change. Bone density decreases at a rate of approximately 1% per month, muscle mass diminishes, cardiovascular function declines as the heart no longer works against gravity to pump blood. The immune system becomes less effective, fluid shifts toward the head, affecting vision and potentially causing brain changes. Even with intensive exercise regimens, these effects continue throughout a mission, raising serious concerns about human viability on journeys lasting years. Life support systems represent yet another technological hurdle. Humans require approximately 800 grams of oxygen, 2 liters of water, and 1 kilogram of food daily. For a crew of 4 on a 3-year mission, this would amount to nearly 10 metric tons of consumables, not including water for hygiene or spare parts for life support systems. While the International Space Station recycles about 90% of its water and regenerates oxygen through electrolysis, it still requires regular resupply missions from Earth, a luxury unavailable to deep space explorers. Communication across vast distances introduces additional complications. Radio signals travel at the speed of light, creating unavoidable time delays as distance increases. A signal from Mars takes between 4 and 21 minutes to reach Earth, depending on the planet's relative positions. From Jupiter, the delay extends to over 40 minutes one way. These lags make real-time conversation impossible, and emergency assistance from Earth impractical. Astronauts venturing to the outer solar system would need unprecedented autonomy. Psychological factors cannot be overlooked. The longest continuous human presence in space has been the 14-month stay of cosmonaut Valery Polyakov aboard the Mir space station. A mission to Mars would require confinement in a small habitat with the same crew for potentially 3 years. Studies of isolated groups in Antarctic research stations and during space mission simulations suggest that maintaining crew cohesion, motivation, and mental health during such extended isolation poses significant challenges. Let us consider what these limitations mean for specific potential missions beyond Earth orbit. The Apollo lunar landing architecture represents our only experience with human exploration beyond low Earth orbit. Using this approach, with chemical propulsion and spacecraft that do not fully recycle resources, we might reasonably reach Mars, though with significant risk and requiring substantially larger vehicles. With enormous investment and accepting high risk, we might potentially reach Venus or the asteroid belt. But Jupiter, the technological hurdles become formidable. Even using gravitational assists to reduce propellant requirements, a human mission to Jupiter would require either revolutionary propulsion systems or journey times measured in years. The radiation environment around Jupiter is extraordinarily intense, with levels near its moon Europa hundreds of times stronger than near Earth. The life support, psychological, and communication challenges would be proportionally greater than for Mars missions. Saturn, Uranus, and Neptune would be even further beyond our reach with current or near-term technology. While robotic probes have visited these worlds, they did so with minimal payloads, multi-year journey times, and no requirement to return to Earth. A human presence in the outer solar system remains firmly in the realm of science fiction until multiple technological breakthroughs can be achieved simultaneously. The economic dimension of space exploration adds another layer of constraint. The International Space Station, humanity's most expensive single structure, has cost approximately $150 billion over its lifetime. A human Mars mission would likely exceed this cost substantially. Without clear economic returns or international cost sharing, securing funding for ambitious exploration beyond Mars becomes politically challenging in democratic societies with competing priorities. Some have suggested that space resource utilization might change this equation. Asteroids contain vast quantities of valuable metals, including platinum group elements worth thousands of dollars per ounce on Earth. The Moon harbors helium-3, a potential fuel for nuclear fusion reactors. Mars has water ice that could be converted to rocket propellant. If these resources could be economically extracted and either returned to Earth or used to support further exploration, the financial calculus of deep space missions might change dramatically. However, this approach faces a chicken and egg problem. Establishing resource extraction operations in space would require precisely the transportation, infrastructure, and technology that currently limits our reach. The initial investment would be enormous, with returns potentially decades away. No single government or corporation has yet committed to such a long-term, high-risk venture. Looking beyond the solar system introduces challenges of an entirely different magnitude. Our nearest stellar neighbor, Proxima Centauri, lies approximately 4.24 light-years from Earth. At the speed of Voyager 1, our fastest outbound spacecraft, a journey there would take over 70,000 years. Even at the speed of New Horizons, which left Earth faster than any previous spacecraft, the journey would take 60,000 years, dozens of times longer than all of recorded human history. This brings us to perhaps the most fundamental limitation of all, the speed of light itself. According to Einstein's special theory of relativity, no material object can accelerate to or beyond the speed of light, which travels at approximately 300,000 kilometers per second. This cosmic speed limit makes journeys between stars, even the closest ones, extraordinarily time-consuming. While relativity allows for time dilation effects that could reduce experience time for travelers approaching light speed, achieving such velocities would require propulsion technologies and energy sources far beyond anything currently available. Some theorists have proposed concepts like warp drives or wormholes that might circumvent the light speed limitation, but these remain highly speculative and face significant theoretical obstacles. As far as we currently understand physics, interstellar travel within a human lifetime remains beyond our technological horizon. Yet the history of technology cautions us against declaring anything permanently impossible. In 1880, the American astronomer Simon Newcomb published a mathematical proof that heavier-than-air flight was impossible. The Wright brothers proved him wrong 23 years later. In 1920, the New York Times criticized Robert Goddard for his belief that rockets could function in vacuum, suggesting he lacked the knowledge ladled out daily in high schools. 4 decades later, humans were orbiting Earth in spacecraft, propelled by Goddard's principles. Technology advances through both incremental improvements and occasional breakthroughs that reshape what we consider possible. Chemical rockets have improved significantly since the V2, with higher performance fuels, more efficient engines, lightweight materials, and computer-optimized flight profiles. These cumulative enhancements have made spaceflight more reliable and somewhat more affordable, though not fundamentally more capable of deep space exploration. True breakthroughs in space propulsion may require entirely new approaches. Nuclear thermal rockets, which use a nuclear reactor to heat propellant rather than chemical combustion, could potentially double the efficiency of chemical rockets. Ion thrusters, which use electrical energy to accelerate charged particles, achieve much higher efficiency, but at very low thrust levels, making them suitable for long-duration missions but not for launching from planetary surfaces. More exotic concepts include nuclear pulse propulsion, which would use small nuclear explosions to propel a spacecraft, potentially achieving both high thrust and high efficiency. Project Orion, studied in the 1950s and 60s, suggested such a system could reach 5% of light speed, potentially enabling interstellar missions within a human lifetime. However, nuclear test ban treaties and concerns about radioactive contamination have prevented practical development. Solar sails offer another alternative, using the slight but persistent pressure of sunlight to gradually accelerate a spacecraft. Given sufficient time, a solar sail could potentially reach speeds much higher than chemical rockets, without carrying any propellant at all. However, their effectiveness diminishes with distance from the sun, limiting their utility for outer solar system exploration. Breakthrough technologies rarely arrive fully formed. They typically emerge from scientific discoveries that initially seem unrelated to their eventual application. The laser was developed without any clear practical purpose, but now finds applications in everything from eye surgery to DVD players. Similarly, advances in fields like high-temperature superconductors, fusion energy, or quantum physics might eventually enable propulsion systems beyond our current imagination. The constraints we face today are real and substantial. Chemical rockets are fundamentally limited by the energy available in molecular bonds. Radiation shielding conflicts with the need for lightweight spacecraft. Life support systems remain imperfect. Communication delays are imposed by light's finite speed. These limitations shape what missions we can reasonably contemplate with current or near-term technology. Yet these constraints need not define the permanent boundaries of human exploration. They simply define our present horizon. Beyond that horizon lies a vast universe, potentially accessible through technologies yet to be developed, based on scientific principles both known and still to be discovered. What appears impossible today may become routine tomorrow. This has been the pattern throughout the history of human exploration and technological development. The ocean-crossing voyages that seemed extraordinary to early seafarers became commonplace with improved shipbuilding. Air travel, once the exclusive domain of the wealthy and adventurous, is now an everyday experience for millions. Space travel may follow a similar trajectory, with current limitations giving way to new possibilities as technology advances. The true limits of human space exploration will ultimately be determined not just by physics and engineering, but by our collective will to push beyond current boundaries. The challenges are immense, the costs substantial, the risks significant. But throughout history, humans have consistently chosen to explore, to discover, to venture into the unknown despite obstacles that once seemed insurmountable. Consider also the computational challenges of deep space missions. As spacecraft venture farther from Earth, the time delay in communications means they must operate with greater autonomy. Current computer systems on spacecraft are typically hardened against radiation, but significantly less powerful than consumer electronics on Earth. The radiation environment of space causes random bit flips and potential system failures, requiring triple redundant systems and extensive error checking. Developing artificial intelligence capable of making critical decisions during weeks or months without human input presents both technical and ethical challenges that we have only begun to address. Power generation represents another constraint on our exploration capabilities. Most spacecraft rely on solar panels, which become progressively less effective as distance from the sun increases. At Mars, solar intensity is less than half that near Earth. By Jupiter, it drops to about 4%. Missions to the outer solar system like Voyager, Cassini, and New Horizons have relied on radioisotope thermoelectric generators, which convert heat from decaying plutonium into electricity. However, these produce relatively modest power output and depend on plutonium-238, which is in limited supply. Developing safe, high-power, long-duration energy sources for deep space missions remains a significant technological challenge. The materials used in spacecraft construction also face limitations. Conventional aerospace materials like aluminum alloys and carbon composites have been optimized for Earth orbit conditions, but may not perform as well during decades-long missions exposed to extreme temperature variations, micrometeoroid impacts, and radiation. Developing novel materials that remain reliable over such timescales, without adding prohibitive mass presence, yet another engineering challenge. As we contemplate the vast distances of our solar system and the even greater gulfs between stars, we should remember that our current technological limitations are not necessarily permanent barriers. They are challenges awaiting solutions, horizons that may expand as our knowledge and capabilities grow. The question is not simply what we can achieve with today's technology, but what might become possible if we continue to pursue the dream of reaching farther into the cosmic ocean that surrounds us. Perhaps the most important thing to understand about our current technological limitations is that they are not static. They evolve as our knowledge and capabilities grow. The seemingly insurmountable barriers of today may become the routine engineering problems of tomorrow. Just as early aviation pioneers could not have envisioned supersonic flight or space rockets, we cannot fully anticipate how future innovations might transform our ability to explore the cosmos. The history of technology teaches us that predictions about permanent limitations are often proven wrong by human ingenuity and perseverance. Having examined our current technological limitations, let us turn our gaze outward to the next frontiers that await human exploration. For all the challenges we have discussed, there remain destinations within our solar system that lie potentially within our reach. While not easy to access, these worlds offer tantalizing possibilities for extending humanity's presence beyond Earth. The most prominent of these near-term destinations is Mars, the red planet that has captured human imagination for centuries. Mars occupies a special place in our collective vision of space exploration. Located between 1.3 and 2.7 astronomical units from the Sun, depending on its position in orbit, Mars represents a challenging yet potentially achievable target for human missions. Its day is remarkably similar to Earth's at 24 hours and 37 minutes. It experiences seasons due to an axial tilt comparable to our home planet. Its surface gravity is about 38% of Earth's, making it the most Earth-like of all planetary bodies in our solar system aside from Venus, which presents far more hostile surface conditions. The concept of sending humans to Mars is not new. Wernher von Braun, the German rocket engineer who later became a key figure in the American space program, published a detailed Mars expedition plan in 1952, more than 5 years before the first satellite reached orbit. His vision involved a fleet of 10 spacecraft, carrying 70 people on an 800-day mission. While enormously ambitious, even by today's standards, this early concept established the technical foundation that later Mars mission architectures would build upon. NASA has studied human Mars missions since the 1960s. The Soviet Union developed detailed Mars landing vehicle designs before its dissolution. Today, multiple space agencies and private companies maintain Mars programs, with mission architectures becoming increasingly sophisticated as our knowledge of the planet grows through robotic exploration. The journey to Mars presents several key challenges that extend beyond those of lunar missions. First is the matter of distance and travel time. While the Moon can be reached in 3 days, Mars requires a minimum of 6 to 9 months using current propulsion technology. This duration places significant demands on spacecraft systems, life support, and crew psychology. Launch opportunities for Mars missions occur approximately every 26 months, when Earth and Mars align in their orbits to minimize the energy required for transfer. These windows last only a few weeks, creating fixed deadlines that mission planning cannot easily adjust. Missing a launch window means waiting 2 years for the next opportunity, a constraint that adds complexity to mission development. Any human mission to Mars must account for the planet's unique environment. The Martian atmosphere, composed primarily of carbon dioxide, is about 1% as dense as Earth's at sea level. This provides some protection from micrometeorites and cosmic radiation, but not enough to shield humans effectively. The thin atmosphere also means that liquid water cannot exist on the surface under natural conditions, as it would either freeze or immediately begin to boil away. Surface temperatures on Mars average about -60 degrees Celsius, with extremes ranging from a relatively mild 20 degrees Celsius in summer at the equator to -125 degrees Celsius at the winter poles. This requires robust thermal management systems for any surface habitat or vehicle. Dust storms occasionally envelop the entire planet, potentially limiting solar power generation and visibility for weeks or months. Despite these challenges, we have learned much about Mars that makes human missions seem increasingly feasible. Robotic explorers have confirmed the presence of substantial water ice reserves, both at the poles and buried beneath the surface at more temperate latitudes. The soil contains perchlorates that, while toxic to humans, could potentially be processed to extract oxygen. Ancient riverbeds, deltas, and mineral deposits suggest that Mars once had flowing water and a thicker atmosphere, raising tantalizing questions about its past habitability and the possibility of ancient microbial life. Various mission architectures have been proposed for human Mars exploration. Some envision a direct approach, similar to Apollo, with a spacecraft traveling from Earth to Mars, landing and returning without establishing permanent infrastructure. Others advocate a more gradual approach, with cargo missions delivering supplies and equipment before human arrival, potentially including habitat modules, power systems, and even propellant manufacturing facilities that would use Martian resources to produce fuel for the return journey. The most ambitious scenarios involve not just exploration, but settlement, with increasingly self-sufficient outposts that could eventually grow into permanent human communities on another world. While such visions remain speculative, they represent a potential long-term future for humanity as a multi-planetary species. The logistical requirements for Mars missions are substantial. A crew of 4 to 6 astronauts would need life support, food, water, power, medical facilities, scientific equipment, surface mobility, habitation space, and a reliable return vehicle. Estimates suggest that even a minimalist Mars mission would require 50 to 100 metric tons of equipment and supplies in Mars orbit, several times the mass of the International Space Station modules. Transporting such mass to Mars would require either multiple launches of existing rockets or the development of new heavy lift vehicles. NASA's Space Launch System and SpaceX's Starship represent attempts to create rockets with the necessary capacity for Mars missions, though both face significant development challenges. The duration of a Mars mission creates unique psychological challenges. A typical mission profile would involve a 6 to 9 month outbound journey, a surface stay of approximately 500 days, and a 6 to 9 month return trip. This nearly 3-year mission duration far exceeds any previous human spaceflight experience. The crew would need to function autonomously, with communication delays of up to 22 minutes round trip, making real-time conversation with Earth impossible. Studies of isolated groups in analogous environments like Antarctic research stations suggest that such long-duration missions would place extreme stress on crew cohesion and mental health. Careful crew selection, training, habitat design, and psychological support systems would be essential for mission success. Radiation exposure represents perhaps the most serious health risk for Mars astronauts. A round-trip mission using current propulsion technology would expose crew members to radiation doses approaching or potentially exceeding NASA's career limits. Galactic cosmic rays, consisting of high-energy particles from distant sources like supernovae, are particularly concerning because they can penetrate even substantial shielding and cause cellular damage, potentially leading to cancer and other health issues years after exposure. Various shielding concepts have been proposed, from water-jacketed spacecraft to magnetic fields that mimic Earth's natural protection. However, all face challenges in terms of mass, power requirements, or technological readiness. Some mission architectures include artificially induced hibernation or torpor states that might reduce metabolic activity and potentially limit radiation damage, though such approaches remain highly speculative. Despite these obstacles, Mars continues to beckon as the next logical step in human space exploration. Its relative proximity the potential for in-situ resource utilization, and its scientific value make it the most attractive target beyond the Earth-Moon system. With sufficient investment and technological development, human missions to Mars appear achievable within the next few decades, potentially before the middle of the 21st century. Beyond Mars lie the outer planets, far more challenging destinations that push the boundaries of our technological capabilities. Let us consider Jupiter, the largest planet in our solar system. At its closest approach to Earth, Jupiter lies more than 588 million kilometers away, a distance that would take current spacecraft many months or even years to traverse. Its powerful gravitational field and intense radiation belts present formidable challenges for any spacecraft, particularly those carrying human crews. Jupiter itself has no solid surface for landing, being composed primarily of hydrogen and helium in gaseous and liquid states. However, its system of moons offers potential destinations of extraordinary scientific interest. Foremost among these is Europa, slightly smaller than Earth's moon, with a smooth, icy surface covering a global ocean of liquid water that may contain twice as much water as all of Earth's oceans combined. Europa's ocean, kept liquid by tidal heating from Jupiter's gravitational pull, represents one of the most promising environments for extraterrestrial life in our solar system. The seafloors of Europa might host hydrothermal vents, similar to those on Earth, that support rich ecosystems independent of sunlight. While robots will likely conduct the first explorations of Europa, including potential missions to penetrate its ice shell and sample the ocean beneath, human presence would enable more sophisticated research and potentially even direct observation of this alien sea. The challenges of human missions to Europa are immense. In addition to the distance and travel time, spacecraft would need to contend with Jupiter's radiation environment, which would deliver lethal doses to unshielded humans within hours. Europa receives about 5.4 sieverts of radiation per day, compared to the 2 to 3 millisieverts per day experienced on the International Space Station. This means radiation levels approximately 2,000 times higher than in low Earth orbit, requiring extraordinary shielding or very brief surface operations. Power generation at Jupiter's distance from the Sun presents another hurdle. Solar intensity drops to about 4% of Earth levels, making large solar arrays or nuclear power sources necessary for any substantial operation. The extreme cold of Europa's surface, averaging about -170 degrees Celsius, would challenge thermal management systems and mechanical components. Communication with Earth would involve light time delays of between 35 and 52 minutes round trip, depending on the planet's alignment. This would make any form of real-time mission control impossible, requiring unprecedented autonomy for both human crews and their supporting systems. Ganymede, the largest moon in our solar system, presents another potential target in the Jovian system. Like Europa, it appears to have a subsurface ocean, though buried beneath a thicker ice shell. Its greater size gives it a higher surface gravity, about 15% of Earth's, which might make prolonged human presence somewhat easier than on smaller moons. Importantly, Ganymede orbits outside the worst of Jupiter's radiation belts, receiving only about 10% of the radiation dose that Europa experiences. Saturn, nearly twice as far from the Sun as Jupiter, presents even greater challenges for human exploration. A journey to Saturn would take years rather than months, using current propulsion technology. Yet here too, a fascinating target awaits: Titan, Saturn's largest moon and the only moon in our solar system with a substantial atmosphere. Titan's atmosphere is primarily nitrogen, similar to Earth's in composition, though not in density. Its surface pressure is about 1.5 times that of Earth at sea level, and surface temperatures hover around -180 degrees Celsius. These frigid conditions mean that water exists only as rock-hard ice, while hydrocarbons like methane and ethane can exist in liquid form. Indeed, Titan has been shown to have lakes and seas of liquid methane and ethane, the only stable bodies of surface liquid known beyond Earth. It also features river networks, shorelines, and weather patterns involving methane rain, creating an eerily Earth-like hydrological cycle using different chemical components. The thick atmosphere and distance from the Sun make Titan one of the most protected environments in the outer solar system in terms of radiation exposure. The atmospheric pressure would also eliminate the need for pressurized spacesuits, though thermal protection would remain essential in the cryogenic conditions. Titan's gravity, at about 14% of Earth's, is similar to that of our Moon, suggesting that long-term physiological effects might be manageable. The scientific value of human exploration of Titan would be enormous. Its complex organic chemistry, including compounds considered precursors to life, offers a window into processes that might have occurred on early Earth. The liquid hydrocarbon lakes could harbor novel forms of life using methane as a solvent rather than water, though this remains speculative. Human explorers could conduct experiments and observations far more complex than any robotic mission could accomplish. Yet the challenges remain daunting. The distance to Saturn means approximately 7 to 9 years for a round trip using current propulsion, with no abort options once committed. Solar power becomes impractical at Saturn's distance, requiring nuclear power sources with lifespans measured in decades rather than years. The extreme cold would stress materials and systems beyond our current experience base. Communication delays would stretch to over 2.5 hours round trip at maximum separation. Could humans someday walk on the icy surface of Europa, or sailboats on Titan's hydrocarbon seas? With current technology, such missions lie beyond our capabilities. Yet they do not appear to violate any fundamental laws of physics. With sufficient advances in propulsion, radiation protection, life support, and other key technologies, human exploration of the outer planets might eventually become feasible, though likely not within the 21st century. The asteroid belt, lying between Mars and Jupiter, presents intermediate challenges and opportunities, consisting of millions of rocky and metallic bodies, ranging from dust-sized particles to dwarf planets like Ceres. The asteroid belt contains valuable resources that might someday support human activities throughout the solar system. Missions to near-Earth asteroids, which pass relatively close to our planet, have already been studied in detail and appear achievable with modest extensions of current technology. Such missions could serve as stepping stones to the main asteroid belt, testing technologies and operational concepts for deeper space exploration, while potentially assessing asteroids for future mining operations. Ceres, the largest object in the asteroid belt at about 940 kilometers in diameter, shows evidence of subsurface water ice and possibly a weak internal ocean. As a dwarf planet with enough gravity to have pulled itself into a roughly spherical shape, Ceres might someday serve as an outpost for human activities in the middle solar system, though its surface gravity of only 3% of Earth's would present significant challenges for long-term habitation. The moons of Mars, Phobos, and Deimos represent another potential stepping stone. These small, irregularly shaped bodies orbit close to Mars and might serve as staging locations for surface missions or as sites for fuel depots and communication relays. Their minimal gravity wells make them easy to reach from Mars orbit and easy to depart from when returning to Earth, potentially simplifying mission architectures. For all these destinations, the common thread of challenge remains the harsh reality of distance. Our solar system is vast beyond easy comprehension. Even with substantial improvements in propulsion technology, journey times to the outer planets would remain measured in years rather than months. Life support systems would need to function flawlessly for durations far beyond our current experience. Psychological and physiological effects of extended spaceflight would push human adaptation to new limits. Yet the history of exploration teaches us that humans will venture wherever it becomes possible to go, driven by curiosity, ambition, and the fundamental desire to see what lies beyond the next horizon. If we can develop the necessary technologies, if we can solve the challenges of radiation, microgravity, and autonomous operation, then human footprints, or their robotic extensions, may someday mark the icy surfaces of worlds orbiting giant planets. When considering potential timelines for such exploration, we must balance optimism with realism. The Apollo program took 8 years from President Kennedy's commitment to the first lunar landing, building on decades of prior research in rocketry and spaceflight. A human Mars mission would be significantly more complex, likely requiring 15 to 20 years of focused development from a firm commitment to landing. Missions to Jupiter's moons might follow 20 to 30 years after the establishment of a human presence on Mars, assuming steady technological progress and sustained funding. Saturn's moons might remain beyond practical human reach until the latter part of the 22nd century, barring revolutionary breakthroughs in propulsion or life support. These timelines assume a gradual, evolutionary approach to solar system exploration. revolutionary technologies could accelerate the process dramatically. For instance, if nuclear fusion propulsion became practical, journey times to the outer planets could potentially be reduced from years to months. If effective hibernation or suspended animation techniques were developed for humans, the life support and psychological challenges of long-duration missions might be substantially reduced. The economics of space exploration will also shape our future reach. The Apollo program cost approximately $25 billion 1960s dollars, equivalent to over $150 billion today. Mars missions would likely cost several times this amount. Without clear economic returns or compelling national security justifications, securing such funding from public sources becomes politically challenging. However, if initial exploration enables the development of space resources, the economic equation might change dramatically. Asteroids contain platinum group metals worth thousands of dollars per ounce on Earth. A single metallic asteroid a kilometer in diameter might contain metals worth trillions of dollars at current market prices. If such resources could be harvested economically, they might fund further exploration, while simultaneously relieving pressure on Earth's environment from terrestrial mining. The outer solar system contains vast reserves of volatiles, including water, ammonia, and hydrocarbons, that could support human activities throughout the solar system. While initially more expensive to access than similar resources from the Moon or asteroids, they might eventually become part of a solar system-wide economy that supports human presence from Mercury to the Kuiper Belt. Beyond economics lies another motivation: ensuring the long-term survival of humanity and Earth's biosphere. A civilization confined to a single planet remains vulnerable to extinction from various catastrophes, both natural and self-inflicted. Spreading human presence throughout the solar system would create redundancy, reducing the risk that a single disaster could end our species or the remarkable diversity of life that evolved alongside us on Earth. This perspective frames space exploration not merely as an adventure or economic opportunity, but as a form of planetary life insurance. The resources, energy, and living space available throughout the solar system could potentially support a civilization far larger and more diverse than what Earth alone could sustain, while reducing human impact on our home planet's fragile biosphere. As we contemplate the next frontiers of human exploration, from Mars to the moons of gas giants, we should recognize that each step outward builds upon what came before. The technologies and operational experience developed for lunar outposts will inform Mars missions. Mars exploration will develop capabilities needed to reach the asteroid belt. Ventures into the asteroid belt will create foundations for exploring the outer planets. This incremental approach, building capability through a series of increasingly ambitious missions, offers the most practical path to expanding human presence throughout the solar system. Each destination presents unique challenges, but also unique opportunities to develop the technologies and techniques needed for the next leap outward. Through robotic precursors, we have already begun this journey. The Curiosity and Perseverance rovers explore Mars today, while earlier missions mapped the planet in detail from orbit. The Galileo spacecraft studied the Jupiter system, while Cassini spent 13 years examining Saturn and its moons. New Horizons gave us our first close look at Pluto and continues into the Kuiper Belt. These robotic emissaries have transformed abstract astronomical objects into real places with landscapes, atmospheres, and histories that we can begin to understand. Human explorers would bring different capabilities to these distant worlds, including adaptability, real-time decision-making, and the uniquely human capacity for wonder and appreciation. While robots will certainly continue to serve as our pioneers, they represent an extension of human curiosity rather than a replacement for human presence. The ultimate goal remains enabling people to directly experience these new worlds, to walk their surfaces, conduct experiments, and see with their own eyes what previously could only be viewed through electronic intermediaries. The challenges are enormous but not insurmountable. With sustained effort, technological innovation, and the collaboration of nations and private enterprises, humans might someday establish a presence throughout much of our solar system. Mars and the asteroid belt appear accessible with foreseeable technology. The moons of Jupiter and Saturn represent more distant but still conceivable goals. Even Uranus, Neptune, and the Kuiper Belt objects beyond might someday feel the touch of human technology. even if direct human presence remains impractical. Our solar system is vast but finite. With sufficient time and technological development, much of it could potentially come within humanity's reach. The true limit to our exploration may ultimately be determined not by physics or engineering, but by our collective will to venture outward, to overcome challenges, and to establish human presence in new and ever more distant environments. As we contemplate these next frontiers, from the rust-colored plains of Mars to the icy shores of Titan's hydrocarbon seas, we should remember that each generation builds upon the achievements of those who came before. The technologies that might someday carry humans to the outer planets will evolve from those being developed today. The scientific understanding that will inform future missions grows with each robotic explorer we send into the void. The journey outward continues, step by step, world by world. Mars beckons as our next destination, challenging yet potentially within reach. Beyond lies a solar system filled with wonders waiting to be explored, each presenting unique challenges, but also unique opportunities to expand the human presence beyond our home world. Having explored the destinations that beckon us beyond Earth, we must now consider how we might reach them more effectively. The limitations of chemical rockets that we discussed earlier represent a fundamental constraint on our ability to explore the solar system, particularly for crewed missions. To truly expand humanity's reach, we need propulsion systems that can deliver greater speed, efficiency, and reliability over the vast distances that separate worlds. The quest for improved space propulsion has occupied scientists and engineers since the earliest days of spaceflight. While chemical rockets remain our primary means of accessing space, a diverse array of alternative propulsion concepts exists at various stages of development. Some are evolutionary improvements on familiar technology, while others represent revolutionary approaches that could fundamentally change our relationship with space travel. Let us explore these technologies, from the nearly operational to the purely theoretical, and consider how they might expand the horizons of human exploration. Nuclear thermal propulsion represents one of the most developed alternatives to chemical rockets. This technology uses a nuclear reactor to heat a propellant, typically liquid hydrogen, which then expands through a nozzle to generate thrust. Because nuclear reactions release millions of times more energy per kilogram than chemical reactions, nuclear thermal rockets can achieve roughly twice the efficiency of the best chemical engines. The United States conducted extensive testing of nuclear thermal rockets during the 1960s and early 1970s under the Nuclear Engine for Rocket Vehicle, Application, or NERVA, program. The most powerful engine tested, called Phoebus 2 Alpha, generated more than 4,400 kilonewtons of thrust and operated for more than 12 minutes. These tests demonstrated the basic viability of the technology, though no nuclear thermal rocket has yet flown in space. The advantages of nuclear thermal propulsion for deep space missions are significant. A crewed Mars mission using this technology could reduce transit time by 30 to 50% compared to chemical rockets, substantially decreasing radiation exposure and psychological stress for astronauts. The higher thrust-to-weight ratio compared to electric propulsion systems makes nuclear thermal rockets suitable for crewed spacecraft, which typically have higher mass and require more rapid acceleration. However, challenges remain. The use of nuclear materials raises safety and political concerns, particularly during launch when an accident could potentially release radioactive material into Earth's atmosphere or surface. The development costs are substantial, and testing is complicated by the need for specialized facilities to contain radiation. Nevertheless, both NASA and DARPA have recently renewed interest in nuclear thermal propulsion for future missions, suggesting this technology may yet play a role in human space exploration. Nuclear electric propulsion takes a different approach, using a nuclear reactor to generate electricity that powers an electric thruster, such as an ion drive or Hall effect thruster. This approach offers even higher efficiency than nuclear thermal rockets, but typically provides much lower thrust, resulting in more gradual acceleration over longer periods. In an ion thruster, atoms of a propellant, often xenon or krypton, are ionized and then accelerated by an electric field to very high velocities before being ejected from the spacecraft. Because the exhaust velocity is much higher than in chemical rockets, the efficiency, or specific impulse, can be 10 to 20 times greater. However, the thrust is typically measured in newtons or even millinewtons rather than the kilonewtons or meganewtons of chemical or nuclear thermal rockets. This low thrust, high efficiency characteristic makes nuclear electric propulsion well suited for robotic cargo missions, where transit time is less critical than fuel efficiency. A large nuclear electric tug could potentially transport supplies and equipment to Mars or the outer planets in advance of human missions, establishing infrastructure before astronauts arrive via faster but less efficient propulsion systems. Several spacecraft have already demonstrated electric propulsion in space, though using solar panels rather than nuclear reactors as their power source. NASA's Dawn mission used ion thrusters powered by solar arrays to orbit both the asteroid Vesta and the dwarf planet Ceres. The European Space Agency's Bepi-Colombo mission to Mercury employs ion thrusters for its 7-year journey. These missions demonstrate the remarkable efficiency of electric propulsion, with Dawn achieving a velocity change of more than 10 kilometers per second using less than 400 kilograms of xenon propellant. Nuclear electric propulsion would extend this capability to the outer solar system, where solar power becomes impractical. A reactor generating hundreds of kilowatts or even megawatts of electrical power could drive multiple high-power thrusters, potentially enabling missions to Jupiter, Saturn, and beyond, with transit times measured in years rather than decades. Solar sails represent a completely different approach to space propulsion, one that requires no propellant at all. A solar sail is a large, lightweight reflective surface that harnesses the pressure of sunlight for propulsion. When photons from the sun reflect off the sail, they impart a small amount of momentum to it. Though this pressure is tiny, about 6.7 micronewtons per square meter at Earth's distance from the sun, it acts continuously and requires no expenditure of mass. A spacecraft using a solar sail would initially accelerate very slowly, but over time could potentially reach velocities far beyond what chemical rockets can achieve. Because no propellant is consumed, a solar sail could theoretically continue accelerating as long as it remains in sunlight, limited mainly by the decreasing intensity of solar radiation with distance. The Japanese space agency JAXA successfully demonstrated solar sail technology with its Ikaros mission, launched in 2010. This spacecraft deployed a 20-meter square sail and used it to adjust its trajectory during a flyby of Venus. NASA and the Planetary Society have also conducted solar sail experiments in Earth orbit, demonstrating deployment mechanisms and measuring the resulting acceleration. For missions within the inner solar system, solar sails offer remarkable efficiency and the potential for trajectories that would be impossible with conventional rockets. A sail spacecraft could maintain a polar orbit above the Sun, providing unique perspectives for solar observation. It could station itself at artificial Lagrange points, creating new vantage points for astronomical observations or communications relays. It could even use the solar sail as a brake to enter orbit around planets without carrying propellant for deceleration. The limitations of solar sails become more pronounced in the outer solar system, where sunlight intensity drops with the square of distance. At Jupiter's orbit, solar pressure is only about 4% of its value near Earth. Beyond Saturn, solar sailing becomes increasingly impractical. However, an advanced concept called a laser sail could overcome this limitation by using ground-based or space-based lasers to provide the photon pressure, potentially enabling much higher accelerations and applications throughout the solar system. Beamed propulsion extends this concept further, using microwave or laser energy transmitted from a fixed location to power a spacecraft. The energy could be used to heat a propellant, as in a thermal rocket, or to drive an electric propulsion system, or to propel a lightweight sail. Because the power source remains stationary, the spacecraft doesn't need to carry it, potentially allowing much higher power-to-weight ratios than self-contained propulsion systems. The most ambitious beamed propulsion concept is Breakthrough Starshot, a research program announced in 2016 that aims to develop the technology to send gram-scale probes to Alpha Centauri at 20% the speed of light, reaching the nearest star system within 25 years of launch. The concept involves using an array of powerful ground-based lasers to accelerate a light sail attached to a miniaturized spacecraft. While primarily focused on interstellar travel, such technology could also revolutionize travel within our solar system, potentially enabling rapid transit to the outer planets. The technical challenges facing beamed propulsion are formidable. The laser array for Breakthrough Starshot would need to generate tens of gigawatts of power, far beyond current capabilities. The sail material would need to be incredibly lightweight, yet able to withstand intense laser illumination without melting or tearing. The spacecraft itself would need to be miniaturized to an unprecedented degree, while still carrying power, communications, and scientific instruments. Nevertheless, no fundamental physical law prohibits this approach, making it a tantalizing possibility for future exploration. Plasma propulsion represents another promising category of advanced propulsion. These systems use electromagnetic fields to accelerate plasma, a state of matter consisting of charged particles, to high velocities. Various types of plasma thrusters exist, including magnetoplasma dynamic thrusters, pulsed plasma thrusters, and variable specific impulse magnetoplasma rockets, commonly known as VASIMR. The VASIMR engine, developed by the Ad Astra Rocket Company, is particularly interesting for future human spaceflight. It uses radio waves to ionize and heat a propellant, typically hydrogen, argon, or xenon, and magnetic fields to accelerate the resulting plasma. The design allows the thruster to vary its specific impulse and thrust, potentially offering both high thrust for rapid acceleration and high efficiency for sustained operation. Theoretical analysis suggests that a VASIMR engine powered by a nuclear reactor or advanced solar arrays could reduce transit time to Mars to as little as 39 days, compared to 6 to 9 months using chemical propulsion. However, such performance would require power levels in the multi-megawatt range, far beyond what current spacecraft can generate. Ground testing has demonstrated the basic principles, but flight demonstrations remain in the planning stages. Tethers represent a unique approach to spacecraft propulsion that leverages the physics of electromagnetic induction. An electrodynamic tether is a conducting wire or tape that can interact with a planet's magnetic field as the spacecraft moves through it. By allowing electrical current to flow through the tether, a force can be generated that either accelerates or decelerates the spacecraft, depending on the direction of the current. In low Earth orbit, electrodynamic tethers could potentially generate electricity by moving through Earth's magnetic field, effectively converting orbital energy into electrical power. Reversing the process, by running current in the opposite direction, could use electricity to boost the orbit. This technology offers the tantalizing possibility of propellantless propulsion for certain orbits, though it requires operation within a planetary magnetic field. Momentum exchange tethers take this concept further, using the conservation of angular momentum to transfer energy between spacecraft. A rotating tether could catch an approaching spacecraft at its lower end, swing it around like a sling, and release it at higher velocity, transferring momentum in the process. The tether system would lose energy in this exchange, requiring periodic reboosts, but could potentially transfer payloads between orbits with minimal propellant use. While tether concepts face significant engineering challenges, including material strength limitations and deployment complexities, small-scale demonstrations have been conducted in orbit. The technology is particularly promising for transportation networks within planetary systems, where repeated operations could amortize the infrastructure costs over many missions. Now we venture into more speculative territory with antimatter propulsion. Antimatter consists of particles identical to normal matter but with opposite charge and quantum properties. When matter and antimatter come into contact, they annihilate each other, converting their entire mass into energy, according to Einstein's famous equation E equals mc squared. This yields the highest energy density of any known reaction, approximately 1,000 times more energetic than nuclear fusion and 100 million times more than chemical reactions. A propulsion system using antimatter annihilation could theoretically achieve exhaust velocities approaching the speed of light, enabling interplanetary journeys in days rather than months or years. Various concepts have been proposed, from pure antimatter rockets to hybrids, where small amounts of antimatter catalyze fusion reactions or heat conventional propellant. The challenges, however, are immense. Currently, antimatter can only be produced in minute quantities using particle accelerators at enormous energy cost. The entire world's production of antimatter amounts to mere nanograms per year, far less than the grams or kilograms that would be needed for propulsion. Storage presents another fundamental problem, as antimatter must be kept isolated from normal matter to prevent premature annihilation. Current electromagnetic traps can hold only tiny amounts and require substantial power and bulky equipment. Despite these obstacles, research continues at institutions like CERN and various universities. While pure antimatter rockets remain firmly in the realm of far future technology, hybrid systems using microscopic amounts of antimatter as a catalyst might become feasible sooner. Even a few micrograms of antimatter could significantly enhance the performance of a conventional nuclear rocket if the energy could be effectively directed. Nuclear fusion, the same process that powers the Sun and other stars, represents another promising avenue for advanced propulsion. In fusion, light atomic nuclei combine to form heavier ones, releasing substantial energy in the process. Compared to nuclear fission, fusion offers higher energy density, less radioactive waste, and the potential for more controllable reactions. Several fusion rocket concepts have been studied, including magnetic confinement fusion rockets, inertial confinement fusion rockets, and magnetized target fusion systems. These would use the high-energy plasma produced by fusion reactions to generate thrust, either directly or by heating a propellant. The direct fusion drive, being developed at Princeton Plasma Physics Laboratory, is one example of this approach. It aims to use a fusion reactor based on the Princeton field reversed configuration to produce both thrust and electrical power. Theoretical studies suggest such a system could reach Pluto in just 4 years, compared to the 9.5 years that New Horizons required. Like many advanced propulsion concepts, fusion rockets require solving significant scientific and engineering challenges. Controlled fusion for energy production remains elusive despite decades of research, though recent advances at facilities like the National Ignition Facility and private ventures such as Commonwealth Fusion Systems show promise. Adapting fusion technology for propulsion adds further complexity, including the need for compact, lightweight reactors and effective heat management in space. The Bussard ramjet, first proposed by physicist Robert Bussard in 1960, represents a different approach to fusion propulsion. This theoretical spacecraft would collect hydrogen from the interstellar medium using an enormous electromagnetic field, funnel it into a fusion reactor, and use the energy for propulsion. Because the spacecraft collects its own fuel during flight, it could theoretically accelerate indefinitely, potentially reaching a significant fraction of light speed for interstellar journeys. Detailed analysis has identified significant challenges with this concept. The density of hydrogen in interstellar space is extremely low, requiring a collection area hundreds of kilometers in diameter to gather useful quantities. The drag created by collecting this material may exceed the thrust produced, particularly at the lower velocities during the initial acceleration phase. The fusion reactions involving the particular isotopes available in space may not yield useful energy given the constraints of a propulsion system. Modified concepts, such as the Ram-augmented interstellar rocket, which carries its own initial fuel supply but collects additional material during flight, may prove more feasible. However, all variants of the ramjet concept remain theoretical, with significant questions about their practicality, even with far future technology. At the furthest edges of theoretical physics lie concepts like the Alcubierre warp drive. Proposed by Mexican physicist Miguel Alcubierre in 1994, this speculative concept would use exotic matter with negative energy density to warp space-time, contracting space in front of the spacecraft and expanding it behind. The ship itself would remain within a bubble of normal space-time, never locally exceeding the speed of light, yet potentially achieving effective faster than light travel from an external perspective. The original mathematics of the Alcubierre metric required vast amounts of negative energy, more than the entire mass energy of the observable universe. Subsequent refinements of the theory have reduced this energy requirement somewhat, but it remains far beyond anything we can currently produce or manipulate. Perhaps more fundamentally, we have no experimental evidence that matter with the necessary negative energy properties can exist in the quantities required, though quantum field theory does predict certain negative energy phenomena on microscopic scales. Even if the energy requirements could be met and suitable exotic matter identified, significant theoretical questions remain about the stability of warp bubbles, the ability to control them from within, and whether causal paradoxes might arise from apparent faster-than-light travel. The Alcubierre drive remains firmly in the realm of theoretical physics rather than practical engineering, though it continues to inspire research at the boundaries between general relativity, quantum mechanics, and cosmology. Other exotic propulsion concepts include quantum vacuum thrusters, which attempt to exploit the properties of the quantum vacuum for propulsion, and gravity manipulation technologies that would alter or shield against gravitational forces. Both face fundamental theoretical objections from mainstream physics and lack experimental verification. While continued research into fundamental physics may someday open new possibilities, these approaches cannot currently be considered viable propulsion technologies. Given this wide spectrum of propulsion options from the nearly practical to the purely theoretical, what might we realistically expect to see deployed in coming decades? Near-term advances will likely come from nuclear thermal rockets, higher power electric propulsion, and possibly small-scale solar sails. These technologies require no fundamental physics breakthroughs, only engineering development and political will. Medium-term advances might include nuclear electric propulsion with megawatt-class reactors, advanced plasma drives, and possibly fusion propulsion if current research trends continue successfully. These would require significant technological advances but no fundamental scientific revolutions, potentially becoming available in the latter half of the 21st century. Far future technologies like antimatter catalyzed propulsion, Bussard ramjets, or concepts not yet imagined would require either fundamental breakthroughs in physics or engineering capabilities far beyond our current horizon. While we cannot rule out such advances, neither can we responsibly plan exploration architectures that depend on them. The practical impact of improved propulsion on human space exploration would be profound. Consider Mars missions as an example. With chemical propulsion, transit times of 6 to 9 months each way result in missions lasting approximately 3 years, including surface stay. This duration drives requirements for life support systems, radiation protection, psychological support, and overall system reliability. Nuclear thermal propulsion could potentially reduce transit times to 3 to 4 months each way. This would not only decrease total mission duration, but would significantly reduce radiation exposure and psychological stress. The propulsion system's higher thrust would also provide more abort options during the Earth departure phase, enhancing crew safety. Nuclear electric or advanced plasma propulsion might reduce transit times further, potentially to as little as 1 to 2 months with sufficiently powerful systems. This would fundamentally change the nature of Mars exploration, transforming it from a rare, flag-planting endeavor into a more routine operation akin to Antarctic research expeditions. Regular crew rotations would become practical, allowing continuous human presence without requiring individual astronauts to commit to multi-year missions. For the outer planets, the impact would be even more dramatic. Chemical propulsion renders human exploration of Jupiter's moons nearly impossible due to transit times of many years. Nuclear thermal propulsion might reduce this to perhaps 2 years round trip. Still extremely challenging, but potentially within the realm of possibility, with advanced life support and radiation protection. Nuclear electric or fusion propulsion could potentially reduce transit times to the Jupiter system to months rather than years, bringing these fascinating worlds within practical human reach. Saturn's moon Titan, with its lakes of liquid methane and dense nitrogen atmosphere, might become a viable destination for human exploration rather than relegated to robotic missions alone. Breakthrough propulsion physics, should it ever become reality, would transform our relationship with the solar system entirely. Transit times between planets would be reduced to weeks, days, or even hours in the most optimistic scenarios. The entire solar system would become accessible for human exploration and potentially settlement, limited more by the habitability of destinations than by the difficulty of reaching them. Beyond faster transit, advanced propulsion enables larger payloads, more robust mission architectures, and greater safety margins. A propulsion system with 10 times the efficiency of chemical rockets could deliver 10 times the payload mass to a given destination with the same initial mass in Earth orbit. This could mean larger habitats, more comprehensive scientific equipment, or redundant critical systems that enhance crew safety. Alternatively, the same payload could be delivered with a much smaller initial mass, reducing launch costs and simplifying mission logistics. This economic aspect of advanced propulsion is often overlooked, but may prove crucial for sustained exploration programs operating under budget constraints. For robotic exploration, which will continue to pioneer our understanding of the solar system regardless of human presence, advanced propulsion offers similar benefits. Missions that currently take decades could be completed in years. Complex multi-flyby trajectories that require precise gravitational assists might be replaced with more direct routes, simplifying mission planning and reducing risk. Sample return missions from distant targets, currently considered extremely challenging, might become routine. As we contemplate how far humanity might travel in space, propulsion technology stands as perhaps the single most important enabling factor. The distances involved in space exploration are so vast that even modest improvements in propulsion capability can dramatically expand our effective reach. Conversely, without significant advances beyond chemical rockets, human presence may remain largely confined to the Earth-Moon system, with only occasional brief excursions to Mars representing our furthest reach. The good news is that multiple promising propulsion technologies exist at various stages of development. None requires overturning fundamental physical laws, though many demand substantial engineering advances and significant investment. With sustained commitment to research and development, humankind could develop the propulsion capabilities needed to explore much of our solar system directly, rather than only through robotic intermediaries. Perhaps the wisest approach is a phased development strategy that pursues incremental improvements in parallel with research into more revolutionary concepts. Nuclear thermal propulsion, with its extensive historical testing and relatively modest technological leap beyond chemical rockets, could provide an important near-term capability enhancement while more advanced systems continue development. Similarly, higher power electric propulsion building on existing ion and Hall effect thruster technology could support cargo missions throughout the inner solar system, establishing infrastructure that later human missions would utilize. Solar sails could demonstrate propellantless propulsion for specialized applications, providing operational experience with an entirely different approach to space travel. Research into fusion, antimatter, and other advanced concepts should continue in parallel, with expectations appropriately calibrated to their technological readiness levels. History shows that seemingly impossible technologies sometimes mature faster than expected, while others encounter unforeseen obstacles. A diverse research portfolio provides the best chance of breakthrough advances, while ensuring practical progress continues regardless. As we develop these technologies, we should remember that propulsion represents only one of many challenges facing deep space exploration. Life support, radiation protection, artificial gravity, and reliable long-duration systems all require similar attention. Nevertheless, propulsion stands as a gatekeeper capability, without which even perfection in other areas cannot enable exploration beyond our immediate vicinity. The quest for improved space propulsion connects directly to our earlier question: how far can humanity travel? With chemical rockets alone, our reach remains limited primarily to the Earth-Moon system, with Mars representing an extreme boundary for human exploration. With nuclear thermal or advanced electric propulsion, the inner solar system opens to us, with Mars becoming reasonably accessible and the asteroid belt at least theoretically within reach. With fusion or comparable advanced technologies, should they prove practical, Jupiter and Saturn's systems might come within our grasp, along with much shorter transit times to closer destinations. Beyond Saturn, even these advanced systems face increasing challenges due to the vast distances involved, though robotic precursors using similar technology could explore even the most distant reaches of our solar system. True interstellar travel to even the nearest stars requires propulsion capabilities far beyond our current technology. Concepts like breakthrough starshot, using beamed energy to accelerate miniature probes to a significant fraction of light speed, may eventually extend our robotic reach to neighboring star systems. Human interstellar travel remains firmly in the realm of far future technology, requiring either multi-generational voyages or fundamental breakthroughs in physics and engineering that we cannot currently anticipate. Yet the history of technology teaches humility about declaring permanent limitations. The space of what becomes possible expands with human knowledge and capability, often in ways difficult to predict from our current vantage point. As we develop new propulsion technologies, we simultaneously expand both our physical reach into the cosmos and our understanding of what might ultimately be possible in the future. The journey to develop these technologies will not be simple or linear. It will involve setbacks, unexpected discoveries, and competing approaches. It will require sustained commitment, despite shifting political winds and economic pressures. Yet it represents perhaps our best hope for expanding humanity's presence beyond Earth and exploring the extraordinary diversity of worlds that surround us. From nuclear rockets to light sails, from fusion drives to exotic physics, the quest for better propulsion continues. Each advance brings more of the solar system within our reach, unveiling new possibilities for exploration and discovery. While the ultimate limits of human travel may remain unclear, the path toward expanding those limits becomes more defined with each technological step forward. Having explored evolutionary improvements to space propulsion, we now turn to potentially revolutionary technologies that might fundamentally transform our ability to travel through space. These breakthrough concepts represent not merely incremental advances but paradigm shifts in how we approach the challenge of interplanetary and potentially interstellar travel. While more speculative than the technologies we have already discussed, these concepts have solid theoretical foundations and active research programs exploring their feasibility. Let us begin with Project Starshot, one of the most ambitious yet potentially achievable breakthrough propulsion concepts currently under development. Announced in 2016 with a $100 million research commitment from the Breakthrough Initiatives, Starshot aims to develop the technology to send gram-scale spacecraft to Alpha Centauri at 20% of the speed of light, reaching our nearest stellar neighbor within 25 years of launch. The concept employs a light sail propulsion system, but with a crucial difference from conventional solar sails. Rather than relying on the diffuse pressure of sunlight, Starshot would use an Earth-based laser array generating many gigawatts of power to illuminate a sail just a few meters across. This concentrated energy would accelerate a miniaturized spacecraft, or Starship, to unprecedented velocities within minutes. At 20% of light speed, or about 60,000 kilometers per second, a Starshot probe would pass Pluto's orbit in less than 3 days, compared to the 9.5 years New Horizons required. It would reach Alpha Centauri in about 25 years, compared to the tens of thousands of years that would be required using our current fastest spacecraft. The technical challenges facing Project Starshot are immense, but not insurmountable. The laser array would need to generate between 1 and 100 gigawatts of power and maintain perfect beam coherence over vast distances. The sail material would need to be incredibly lightweight, yet able to withstand intense laser illumination without melting, tearing, or becoming opaque. The spacecraft would need extreme miniaturization of all components, including power systems, sensors, computers, and communication equipment. Perhaps most challenging is the communication system. A gram-scale probe reaching another star would need to transmit data back to Earth across 4 light-years of interstellar space. Current concepts propose using the sail itself as a transmitting antenna and the same laser array that launched the probe as a receiver, but the power and pointing requirements remain daunting. What makes Starshot particularly interesting is that many of the component technologies already exist or are developing rapidly. Advances in nanotechnology continue to shrink electronic components and sensors. Material science has produced increasingly lightweight, yet strong materials suitable for sails. Photonics has developed high-power lasers and beam control techniques. Each of these fields continues to advance independently, potentially converging toward the capabilities Starshot would require. While primarily conceived as an interstellar mission concept, Starshot technology could revolutionize exploration within our solar system as well. Probes accelerated to even a fraction of the proposed interstellar velocity could reach any planet in days or weeks rather than years. A stream of low-cost, mass-produced probes could continuously monitor the entire solar system, providing real-time data about dynamic phenomena like storms on gas giants, volcanic eruptions on Io, or seasonal changes on Mars. The economics of such an approach differ fundamentally from current space missions. The expensive infrastructure, primarily the laser array, would remain on Earth, while the spacecraft themselves could be comparatively inexpensive and launched in large numbers. This might allow for a democratization of deep space exploration, with universities, research institutions, or even private individuals potentially able to fund individual probes once the infrastructure exists. Turning from the tiny to the titanic, we come to another breakthrough concept: the nuclear pulse propulsion system, originally developed under Project Orion. While nuclear thermal rockets use the heat from a controlled fission reaction to expel propellant, nuclear pulse propulsion would use a series of small nuclear explosions behind a massive pusher plate attached to the spacecraft by shock absorbers. Each detonation would impart momentum to the pusher plate, gradually accelerating the vehicle. Studies conducted in the 1950s and 60s suggested that such a system could achieve exhaust velocities around 3 to 5% of light speed, orders of magnitude beyond chemical rockets. This would potentially enable interplanetary travel in weeks rather than months or years, and even open the possibility of interstellar precursor missions reaching nearby stars within a human lifetime. The physics of nuclear pulse propulsion is well understood, and the concept requires no fundamental scientific breakthroughs. However, it faces enormous political and practical challenges. The Partial Nuclear Test Ban Treaty of 1963 prohibited nuclear explosions in the atmosphere, outer space, and underwater, effectively halting development of the Orion concept. Environmental concerns about launching such a vehicle from Earth's surface are substantial, and the public perception of launching thousands of nuclear devices into space presents a nearly insurmountable political barrier. Moving to the realm of theoretical physics, we encounter the concept of the Alcubierre warp drive. First described by Mexican physicist Miguel Alcubierre in 1994, this speculative propulsion system would manipulate space-time itself rather than moving an object through space in the conventional sense. The Alcubierre metric describes a bubble of warped space-time that contracts the fabric of space in front of a spacecraft while expanding it behind. The vehicle itself would remain within a region of flat space-time, experiencing no acceleration, while the bubble would effectively carry it at velocities that could exceed the speed of light from an external reference frame. Importantly, this would not violate Einstein's special relativity, because the spacecraft itself would not be moving faster than light through local space, only riding a wave of warped space-time. The concept resembles a surfer riding an ocean wave. The surfer moves with the wave but is not himself paddling at the wave's velocity. Similarly, a spacecraft in an Alcubierre bubble would be carried by the distortion of space-time rather than moving through space in the conventional sense. The theoretical challenges facing the Alcubierre drive are formidable. The original metric required exotic matter with negative energy density to create the necessary space-time curvature. The amount of negative energy required in Alcubierre's initial calculations was equivalent to more than the entire mass energy of the observable universe, clearly beyond any foreseeable technology. Subsequent refinements by physicists, including Harold White at NASA, have suggested that modifying the shape of the warp bubble could dramatically reduce the energy requirements, potentially to levels equivalent to the mass energy of an object the size of the Voyager spacecraft. While still beyond our technological capabilities, this at least brings the concept from the utterly impossible to the merely extraordinarily difficult. Even with the energy problem solved, fundamental questions remain about the Alcubierre drive. Could such a bubble be created from within, or would it require external manipulation of space-time? How would a spacecraft within the bubble navigate or control its trajectory? Would the leading edge of the bubble interact with particles in interstellar space, potentially causing dangerous radiation inside the bubble? Could such a system avoid creating closed time-like curves that might allow causality violations? The theoretical possibility of wormholes represents another potential breakthrough in space travel. Einstein's general theory of relativity allows for the existence of tunnels through space-time that could connect distant regions, potentially enabling rapid transit between them. If stable, traversable wormholes could exist, they might allow nearly instantaneous travel between planets, stars, or even galaxies, regardless of the normal space distance between them. Wormholes appear in the mathematics of general relativity as Einstein-Rosen bridges, first described in 1935. However, natural wormholes would be unstable, collapsing instantly before anything could pass through them. Keeping a wormhole open would, like the Alcubierre drive, require exotic matter with negative energy to counteract this tendency to collapse. Physicist Kip Thorne and his colleagues at Caltech have extensively studied the theoretical properties of traversable wormholes. Their work suggests that if exotic matter with the necessary properties could be produced in sufficient quantities, and if quantum gravitational effects don't invalidate the macroscopic predictions of general relativity, then stable wormholes might be possible in principle. The challenges, however, are at least as daunting as those facing the Alcubierre drive. We have no experimental evidence that exotic matter with the necessary properties can exist in macroscopic quantities. Creating and manipulating such a wormhole would require technological capabilities far beyond our current horizon. The energy requirements would be enormous, and the precision of control needed to maintain stability would be extraordinary. For practical space mission planning, the distinction between these categories is crucial. NASA, ESA, and other space agencies must balance aspirational research into breakthrough concepts with realistic technology development that can enable missions within programmatic timeframes. Commercial space companies face even more stringent financial constraints, focusing primarily on technologies with clear paths to revenue generation. Nevertheless, research into breakthrough propulsion physics deserves continued support, even if modest in scale. The potential returns from even one viable breakthrough concept could transform humanity's relationship with space, enabling exploration and potentially settlement throughout the solar system or beyond. Just as early aeronautics research eventually enabled global air travel and nuclear physics research led to both weapons and power generation, fundamental research in propulsion physics may yield applications both expected and unexpected. As we contemplate how far humanity might travel, these breakthrough technologies represent our most ambitious possibilities. While current and near-term technology might enable human exploration of Mars and robotic exploration of the outer solar system, breakthrough propulsion could potentially open the entire solar system to human presence and the nearest stars to robotic exploration within a human lifetime. The gap between physics and engineering remains substantial for most breakthrough concepts. Our theoretical understanding suggests tantalizing possibilities, but translating equations on paper to functional hardware in space requires solving innumerable practical challenges. Yet the same could once have been said of heavier-than-air flight, nuclear energy, or space travel itself. Perhaps the most important insight from studying breakthrough propulsion physics is recognizing that our current technological constraints may not represent permanent limitations. The horizon of possibility continues to evolve with our understanding of the universe. While we cannot count on speculative breakthroughs to solve immediate challenges, neither should we assume that today's limitations will forever constrain human exploration of space. The most promising breakthroughs may come not from the concepts we have already imagined, but from discoveries yet to be made. Just as general relativity and quantum mechanics revolutionized physics in ways their predecessors could not have anticipated, future theoretical advances may reveal propulsion possibilities we cannot currently envision. As we reach toward the stars, breakthrough technologies represent our most ambitious hopes for expanding human presence beyond the immediate vicinity of Earth. While many remain speculative, they remind us that the boundaries of the possible continue to expand with human knowledge and ingenuity. The ultimate limits of how far we might travel remain unknown, defined not just by the physics we understand today, but by what we might discover tomorrow. As we drift through the quiet depths of our contemplation, let us now ponder perhaps the most profound question in our journey. Could humanity ever truly leave our solar system? Could we venture into the vast interstellar void, crossing the enormous gulfs between stars to reach new solar systems with their own planets, moons, and potentially habitable worlds? This question touches not just on technology and physics, but on the very nature of human ambition and our potential future as a spacefaring species. To frame this question properly, we must first appreciate the almost incomprehensible scale of interstellar space. The nearest star system to our Sun, Alpha Centauri, lies approximately 4.3 light-years away. This means that light itself, traveling at 300,000 kilometers per second, requires 4 years and 3 months to make the journey. The distances involved dwarf anything we have previously discussed within our solar system by orders of magnitude. To put this in perspective, Voyager 1, currently the most distant human-made object from Earth, has been traveling for over 45 years and has journeyed approximately 23 billion kilometers, or about 155 astronomical units from our planet. Moving at approximately 17 kilometers per second relative to the Sun, It became the first spacecraft to enter interstellar space when it crossed the heliopause, the boundary where the sun's solar wind is stopped by the interstellar medium, in 2012. Yet despite this remarkable achievement, Voyager 1 has covered only about 0.002 light-years, less than 1/2000th of the distance to Alpha Centauri. At its current velocity, it would require approximately 70,000 years to reach our nearest stellar neighbor. Voyager was never designed for interstellar travel, of course, but this calculation illustrates the fundamental challenge. The fastest object humans have ever built would take longer than all of recorded human history to reach even the closest star. The Pioneer 10 and 11 spacecraft, launched in the early 1970s, and Voyager's twin, Voyager 2, are also on trajectories that will eventually take them into interstellar space, never to return. New Horizons, which performed the first close flyby of Pluto in 2015, is also destined for interstellar space, though it will not overtake the Voyagers since they had the advantage of gravity assists from the giant planets that accelerated them to higher velocities. These 5 spacecraft represent humanity's first tentative physical presence beyond our solar system, though it is a presence that will remain silent and uncontrolled once their nuclear power sources no longer generate enough electricity to operate their systems. Voyager 1 is expected to fall silent around 2025, after nearly 50 years of operation. They will continue their journeys regardless, eventual emissaries from Earth passing near distant stars tens of thousands of years in the future. This brings us to our first important insight about interstellar travel. We have already accomplished it, in a limited sense. Human artifacts are currently traveling through interstellar space and will eventually pass near other stars. The question is not whether we can reach other stars at all, but whether we can do so in timeframes and with capabilities that would make the journeys meaningful for human civilization. Let us consider what would be required for more ambitious interstellar missions. First, we would need dramatically higher velocities than anything we have achieved to date. Even reducing the travel time to Alpha Centauri from tens of thousands of years to something closer to a human lifespan would require speeds of a significant fraction of the speed of light. For example, at 10% of light speed, approximately 30,000 kilometers per second, the journey would take about 43 years. At 20%, it would take about 22 years, and at 50%, a more reasonable 8.6 years. These velocities are orders of magnitude beyond our current capabilities, but not forbidden by any law of physics. The energy requirements for such missions, however, would be enormous. Accelerating even a relatively small 1,000-kilogram spacecraft to 10% of light speed would require approximately 4.5 times 10 to the 16th joules of energy, equivalent to the entire annual electrical energy production of a country like Germany. Higher velocities would require quadratically more energy according to the kinetic energy equation, with 20% of light speed requiring 4 times as much energy as 10%. This energy challenge represents one of the fundamental barriers to interstellar travel. Chemical rockets are clearly inadequate, with exhaust velocities less than 1/10,000th of light speed. Even advanced propulsion concepts like nuclear thermal, nuclear electric, or fusion rockets would struggle to achieve the necessary performance without enormous propellant mass ratios that would make the spacecraft impractically large. Concepts like the laser-driven light sail proposed by Breakthrough Starshot might offer a path to these velocities for small payloads, as we discussed earlier. By leaving the power source behind and using a concentrated beam of laser light to accelerate a lightweight sail, such a system could potentially achieve velocities of 20% of light speed or higher for gram-scale spacecraft. For larger payloads, and particularly for human missions, nuclear pulse propulsion remains one of the few approaches that could theoretically achieve a few percent of light speed with foreseeable technology. Studies of Project Orion derivatives suggested that velocities up to about 8% of light speed might be achievable for spacecraft with thousands of nuclear devices, though such missions would face enormous political, safety, and engineering challenges. Antimatter propulsion, while still highly speculative, given our current inability to produce or store significant quantities of antimatter, could theoretically achieve even higher velocities. The energy density of matter, antimatter, annihilation, converting mass directly to energy according to Einstein's famous equation, would enable exhaust velocities approaching the speed of light itself. However, the practical challenges of antimatter production, storage, and controlled reaction appear insurmountable with any near-term technology. Beyond the propulsion challenge lies another fundamental problem for interstellar travel: the interstellar medium itself. While space is often described as a vacuum, interstellar space contains approximately 1 atom per cubic centimeter, primarily hydrogen. At the velocities required for interstellar travel within a human lifetime, these atoms would strike the spacecraft with enormous energy, potentially causing significant erosion and radiation. At 10% of light speed, each hydrogen atom would impact with kinetic energy of about 5,000 electron volts, equivalent to soft X-rays. At higher velocities, the energy increases quadratically, with atoms striking like cosmic rays at 20% of light speed or higher. Shielding against this radiation flux would require substantial mass, working against the need for lightweight vehicles to achieve high velocities. Various solutions have been proposed, from physical shields made of beryllium or other materials to magnetic fields that would deflect charged particles. The most effective approach might be an ablative shield that gradually erodes during the journey, sacrificing mass to protect the spacecraft behind it. However, all these approaches add complexity, mass, and potential failure modes to an already challenging mission concept. For robotic missions, the challenges are substantial, but potentially solvable with sufficient technological development. Small, lightweight probes with minimal functionality might be sent at significant fractions of light speed using beamed energy propulsion. More capable robotic missions might travel more slowly, perhaps at a few percent of light speed, using nuclear or other advanced propulsion. These would take centuries rather than decades to reach nearby stars, but could still provide valuable scientific data if designed for sufficient longevity. For human missions, however, the challenges multiply dramatically. In addition to the propulsion and shielding requirements, a crewed interstellar spacecraft would need to support human life reliably for years or decades, without any possibility of resupply or rescue. The life support systems would need to be extraordinarily reliable, with multiple layers of redundancy and the ability to be repaired using only onboard resources. Provision of food, water, and oxygen for such extended durations would almost certainly require a closed-loop ecological system that could recycle all wastes and regenerate consumables indefinitely. Such systems have been studied extensively, but never demonstrated at the reliability levels that would be required for interstellar travel. Experiments like Biosphere 2 attempted to create closed ecological systems, but encountered numerous difficulties maintaining stable conditions, even with the ability to receive outside assistance. The psychological challenges of interstellar travel for human crews would be equally daunting. The isolation would be far more extreme than anything previously experienced in space, or even in analogous Earth environments like Antarctic research stations. The crew would need to maintain mental health and cohesion for decades, while confined to a relatively small habitat, with communication delays to Earth eventually stretching to years as the distance increased. Various approaches have been proposed to address these challenges, from selecting extremely compatible crew members to designing spacecraft interiors to maximize psychological well-being. Virtual reality or other advanced entertainment systems might help alleviate boredom and provide the sensation of varied environments. Nevertheless, the psychological stress of knowing that Earth is unreachable and help is unavailable would remain a formidable challenge. Radiation exposure represents another critical concern for human interstellar travel. Beyond the solar system, the protective influence of the sun's magnetic field is absent, exposing spacecraft to the full intensity of galactic cosmic rays. These high-energy particles can penetrate substantial shielding and cause cellular damage, potentially leading to cancer and other health effects over time. For journeys lasting decades, the cumulative radiation dose could exceed safety limits unless substantial shielding is provided. However, massive shielding works against the need for high velocity. Active shielding using magnetic fields has been proposed, but would require significant power and adds its own complexity. The radiation challenge alone might render conventional human interstellar travel impractical, without substantial advances in either shielding technology or human biology. This brings us to several alternative approaches to human interstellar travel that might circumvent some of these challenges. The first is the generation ship concept, where the original crew would not survive to reach the destination. Instead, their descendants, born and raised aboard the spacecraft, would eventually arrive at the target star system after a journey lasting centuries or even millennia. Generation ships would essentially be traveling space colonies, large enough to support a stable human population over many generations. They would need to be enormous compared to conventional spacecraft, potentially kilometers in scale, with carefully designed ecological, social, and governance systems to maintain stability over centuries. The ethical questions surrounding such missions are profound, as the descendants of the original crew would have no choice about their participation in the journey. A variation on this approach is the sleeper ship, where most of the crew would remain in suspended animation during the journey, awakening only upon approaching the destination. This would reduce the psychological stress, life support requirements, and social complexity of the mission. However, human hibernation remains firmly in the realm of science fiction. While some promising research exists in inducing torpor states that reduce metabolic rate, true suspended animation that could safely preserve humans for decades or centuries remains speculative. A more radical approach involves sending not humans themselves, but the information needed to recreate them at the destination. This concept, sometimes called digital crew or uploaded consciousness, would require advanced artificial intelligence, mind-uploading technology, and molecular manufacturing capabilities far beyond our current technology, but not obviously prohibited by physical law. In this scenario, a robotic probe carrying the digitized minds of its crew would travel to another star system, establish itself, and then use local resources to build bodies or environments for the stored consciousness patterns. The digital crew could experience the journey in simulation at accelerated rates or remain dormant until arrival. Such an approach would eliminate many of the biological challenges of interstellar travel, but raises profound questions about the nature of consciousness, identity, and what it means to be human. Yet another approach, more pragmatic but perhaps less satisfying, would be to send only robots designed to establish infrastructure at the destination that could later support human settlers arriving on faster ships. These precursor missions would travel relatively slowly, taking centuries to reach nearby stars, but would prepare habitats, gather resources, and possibly even begin terraforming processes that would make subsequent human settlement more viable. All these approaches face enormous technological challenges, yet none violate the known laws of physics. Given sufficient time, resources, and technological development, some form of interstellar travel appears possible in principle, though perhaps not in the form typically depicted in science fiction. The question then becomes not whether we could leave the solar system, but whether we would choose to do so, given the extraordinary costs and challenges involved. The economic case for interstellar travel is difficult to make using conventional metrics. The resources required would be enormous, the timeframes would extend beyond normal investment horizons, and the potential returns would be realized only after decades or centuries, if at all. National prestige, scientific curiosity, or species survival might provide stronger motivations than economic gain. The desire to ensure human continuity in case of catastrophic events in our solar system could justify the enormous expenditure of resources required for interstellar missions. Similarly, the discovery of potentially habitable worlds around nearby stars might galvanize public support for interstellar exploration, despite the costs and timeframes involved. The search for extraterrestrial life represents another compelling motivation for interstellar travel. While astronomical observations can detect certain biosignatures in exoplanet atmospheres, definitive confirmation of life would likely require physical samples or in situ analysis. If evidence of life were detected around a nearby star through telescopic observations, the scientific value of sending probes for closer study would be immense. Let us now consider some specific interstellar mission concepts that have been studied in detail. Project Daedalus, a study conducted by the British Interplanetary Society in the 1970s, proposed a two-stage nuclear pulse propulsion spacecraft using deuterium-helium-3 fusion. The design called for a 54,000-ton initial mass, most of which was fuel, accelerating to about 12% of light speed for a 50-year journey to Barnard's star, about 6 light-years away. Project Longshot, developed by NASA and the US Naval Academy in the 1980s, proposed a smaller nuclear pulse propulsion spacecraft for a mission to Alpha Centauri. It would have taken about 100 years to reach its destination, traveling at about 4.5% of light speed. More recently, Project Icarus has been revisiting these concepts with modern technology and knowledge, examining a range of propulsion options, including various fusion approaches. The Breakthrough Starshot initiative, as we discussed earlier, takes a radically different approach, with its laser-propelled light sails carrying gram-scale star chips. All these concepts make different trade-offs between mission duration, technological readiness, payload capability, and cost. The common thread is the recognition that interstellar travel, while extraordinarily challenging, appears physically possible given sufficient technological development and resource commitment. The timeframes for achieving practical interstellar travel capability remain highly uncertain. Optimistic projections suggest that simple, lightweight probes like those envisioned by Breakthrough Starshot might be feasible within the next few decades, given focused research and development. More capable robotic missions using nuclear or other advanced propulsion might become possible by the end of the 21st century or early in the 22nd. Human interstellar travel, if it proves feasible at all in its conventional form, would likely remain beyond our capabilities until well into the 22nd century or beyond. Generation ships or sleeper ships might represent the earliest approach for physical human presence in other star systems, while digital crew or consciousness transfer approaches would depend on advances in computing and neuroscience that are difficult to predict. As we contemplate these possibilities, we should remember that technological forecasting grows increasingly unreliable beyond a few decades. Attempting to predict what technologies might exist 2 or 3 centuries from now is essentially impossible, as it would have been for someone in the 18th century to anticipate nuclear power, space travel, or the internet. Unexpected breakthroughs could dramatically accelerate the timeline for interstellar capabilities. Conversely, fundamental limitations that we do not yet fully appreciate might render certain approaches permanently impractical, regardless of technological advancement. The only certainty is that our understanding will continue to evolve as science and technology progress. Beyond the question of whether we could physically reach other stars, lies the deeper question of what we might find there and what we might do upon arrival. Astronomical observations have revealed that most stars host planetary systems, many with potentially habitable worlds. The nearest star system, Alpha Centauri, includes 3 stars, at least one of which, Proxima Centauri, is known to host potentially habitable planets. Would we simply observe these new worlds from orbit, perhaps sending landers to study their surfaces and atmosphere? Or would we attempt to establish permanent human presence, creating habitats, or even undertaking the multi-generational project of terraforming planets to make them more Earth-like? These questions of purpose and ethics would shape the form and scale of interstellar missions just as much as the technical challenges. If we discovered evidence of indigenous life, even microbial, how would that influence our approach? Would we establish quarantine protocols to prevent biological contamination in either direction? Would we consider some worlds off limits for human settlement to preserve unique evolutionary pathways? These questions have been explored in science fiction, but would become urgently practical if interstellar travel became feasible. In considering the possibility of leaving our solar system, we confront not just technical challenges but philosophical ones. What is the purpose of human expansion into space? Is it primarily for knowledge, for resources, for ensuring species survival, or for some deeper drive to explore and expand that is intrinsic to human nature? Different answers to these questions might lead to very different approaches to interstellar travel. For all the challenges, interstellar travel represents the logical extension of humanity's journey beyond Earth. Just as we once crossed oceans to discover new continents, just as we now reach toward other planets in our own solar system, someday we may extend our presence to other stars. The timeframes may be longer, the distances vastly greater, but the fundamental urge to explore remains the same. The Voyager spacecraft, silently crossing interstellar space with their golden records, containing sounds and images of Earth, represent humble first steps on this grandest of journeys. In the decades and centuries to come, they may be followed by more sophisticated emissaries, and perhaps eventually by humans in some form, carrying consciousness, if not always, conventional biology to new worlds circling distant suns. Could we leave the solar system? The answer appears to be a qualified yes. With sufficient technological development, resource commitment, and time, some form of interstellar travel seems possible within the constraints of known physics. The form it takes, the timeframes involved, and the extent of human presence in other star systems remain open questions, dependent on future discoveries and societal choices. As we drift through the cosmic ocean, contemplating these vast possibilities, remember that the journey outward has only just begun. From our modest first steps into space less than a century ago, we have already placed primitive emissaries on trajectories that will eventually pass near other stars. What might we accomplish in the centuries and millennia to come, as our knowledge, capabilities, and perhaps our very nature continue to evolve? The stars, distant yet persistent in their shimmer, await. Whether we reach them in our current form, through our machine creations, or in ways we cannot yet imagine, they represent the next great frontier in humanity's age-old journey of exploration and discovery. The path will be longer and more challenging than any we have traveled before, but the destination, should we choose to pursue it, holds wonders beyond our current imagining. As Voyager 1 and its siblings travel silently through the interstellar void, carrying their golden records like messages in bottles cast into a cosmic ocean, they remind us that we have already taken the first tentative steps beyond our solar system. The greater journey, should we choose to undertake it, still lies ahead, beckoning us outward toward distant suns and unknown worlds. As we contemplate journeys to distant worlds, we must recognize that the most significant limitations to human space travel may not be the spacecraft, the propulsion systems, or the vast distances involved. Rather, they may be found within ourselves, in the biological forms and psychological structures that evolved for life on Earth, not for existence in the harsh emptiness between worlds. Our bodies and minds, marvelously adapted for our home planet, face profound challenges when venturing into the alien environment of space. The human body evolved over millions of years under the constant pull of Earth's gravity, protected by our planet's magnetic field and atmosphere from cosmic radiation, and sustained by the complex web of life that provides our air, water, and food. Space presents an environment fundamentally hostile to our biology, lacking all these essential elements of our evolutionary context. Understanding these biological limitations is crucial for assessing how far humans might realistically travel beyond Earth. Let us begin with the most immediately noticeable effect of space on the human body: weightlessness. In the microgravity environment of orbital spaceflight, the body undergoes rapid and significant changes. Without the constant pull of gravity, bones no longer need to support weight, and they begin to lose calcium and weaken, a condition known as osteopenia, or in more severe cases, osteoporosis. Studies on astronauts aboard the International Space Station have shown bone density losses of 1 to 2% per month in weight-bearing bones, particularly in the spine, pelvis, and legs. The muscular system similarly atrophies without the resistance provided by gravity. Muscles that work against gravity on Earth, particularly those in the legs and back, can lose up to 20% of their mass during a typical 6-month stay in orbit. This deconditioning occurs despite rigorous exercise programs designed to counteract it. Upon return to Earth's gravity, astronauts often struggle with basic movements like walking and maintaining posture until their bodies readapt. These effects become increasingly severe with longer durations in space. A journey to Mars, potentially lasting 2 to 3 years round trip, would expose astronauts to microgravity for periods far longer than most have experienced to date. Upon arrival at Mars, they would need to function effectively in the Martian gravity of about 38% of Earth's, potentially after many months of muscle and bone deterioration. Interstellar journeys, measured in decades rather than months, would present even greater challenges. Without some form of artificial gravity, the physical deterioration would likely progress to the point where normal function in any gravitational environment upon arrival might be impossible. The descendants born on generation ships might develop bodies fundamentally different from those of their Earth-evolved ancestors, perhaps entirely unsuited to life on a planetary surface. Artificial gravity could potentially address these issues. The most straightforward approach involves rotating a spacecraft or habitat to generate centrifugal force that mimics gravity. However, practical implementation faces significant challenges. Small diameter rotating structures produce unpleasant Coriolis effects that can cause disorientation and motion sickness. Studies suggest that rotation rates should not exceed 2 revolutions per minute for comfort, which means the rotating structure needs a radius of at least 100 meters to generate Earth-like gravity, requiring spacecraft far larger than anything humans have constructed in space to date. Beyond the musculoskeletal system, microgravity affects virtually every aspect of human physiology. The cardiovascular system, evolved to pump blood against gravity, recalibrates in space. Blood and fluid shift toward the upper body, causing the characteristic puffy-faced appearance of astronauts in orbit. The heart, no longer working against gravity to pump blood to the brain, becomes deconditioned over time. Upon return to gravity, astronauts often experience orthostatic intolerance, an inability to maintain blood pressure when standing, resulting in dizziness and fainting. The fluid shift also increases pressure in the skull, which appears to cause changes to the structure of the eye and brain. Many astronauts returning from long-duration missions report vision problems, a condition now known as Spaceflight-Associated Neuro-Ocular Syndrome, or SANS. Medical imaging has revealed flattening of the eyeball, swelling of the optic nerve, and changes to brain structure following extended time in space. The long-term implications of these changes remain incompletely understood, but they represent potential limitations for lengthy missions. The immune system also functions differently in space. Studies show altered immune responses, with some components becoming hyperactive while others are suppressed. Astronauts show increased vulnerability to infection and reactivation of latent viruses like herpes. The causes appear multifactorial, involving microgravity, radiation exposure, and psychological stress. For interplanetary or interstellar journeys, maintaining effective immune function would be essential, as medical assistance from Earth would be increasingly delayed or unavailable. Perhaps the most significant biological challenge of deep space travel is radiation exposure. On Earth, we are protected from cosmic radiation by our planet's magnetic field and atmosphere. In low Earth orbit, the International Space Station receives some protection from Earth's magnetosphere, though astronauts there still experience radiation doses approximately 100 times higher than on Earth's surface. Beyond the magnetosphere, in interplanetary or interstellar space, radiation levels increase dramatically. Space radiation comes in several forms, each presenting distinct hazards. Solar particle events, essentially radiation storms from the sun, can deliver potentially lethal acute radiation doses without adequate shielding. Galactic cosmic rays, high-energy particles from distant sources like supernovae, are even more challenging to shield against. These particles can penetrate substantial shielding and cause damage to cells, DNA, and electronic equipment. The health risks from chronic radiation exposure include increased cancer risk, damage to the central nervous system, and potential cognitive impairment. NASA estimates that a round-trip Mars mission using current technology would expose astronauts to radiation doses approaching or exceeding career lifetime limits for cancer risk. Interstellar journeys, lasting decades, would increase this exposure proportionally, potentially to lethal levels without revolutionary advances in shielding technology. Conventional shielding approaches face a fundamental limitation. The shield mass required for effective protection against galactic cosmic rays is so substantial that it works against the need for lightweight spacecraft to achieve high velocities. Water, hydrogen-rich plastics, or other materials can provide some protection, but total shielding would require meters of thickness, adding enormous mass to the spacecraft. Active shielding using magnetic fields or plasmas has been proposed as an alternative, mimicking Earth's natural magnetosphere. While theoretically promising, such systems would require significant power and have yet to be demonstrated at the scales necessary for human protection. For truly long-duration missions beyond our solar system, radiation protection represents one of the most formidable biological challenges, potentially requiring fundamental advances in shielding technology or even modifications to human biology itself. The closed environment of a spacecraft presents another set of biological challenges. Humans require approximately 800 grams of oxygen, 2 liters of water, and 1 kilogram of food daily. On a multi-year mission, carrying all these supplies becomes impractical, necessitating regenerative life support systems that can recycle waste products back into usable resources with minimal loss. The International Space Station partially demonstrates such systems, recycling about 90% of its water and regenerating oxygen through electrolysis of water. However, it still requires regular resupply missions. A truly closed ecological system, sustaining human life indefinitely without external inputs, has never been successfully demonstrated. Experiments like Biosphere 2 in the 1990s encountered numerous difficulties, including declining oxygen levels, nutrient cycling problems, and unanticipated ecological interactions. For interstellar journeys lasting decades or generations, life support systems would need unprecedented reliability and complete closure of material cycles. Any small imbalance in resource recycling would compound over time, potentially leading to critical shortages. The ecological complexity required to maintain stable conditions indefinitely might necessitate spacecraft ecosystems far more elaborate than typically envisioned, essentially miniature biospheres rather than merely technological life support systems. Moving beyond purely physiological concerns, we must consider the psychological dimensions of deep space travel. The human mind, like the body, evolved in a specific environment and faces unique challenges when removed from its natural context. Extended isolation, confinement, and extreme environments produce well-documented psychological effects that would be amplified during interplanetary or interstellar journeys. Studies of personnel in analogous environments like Antarctic research stations, submarine crews, and simulated Mars missions have identified several consistent psychological challenges. These include depression, anxiety, sleep disorders, interpersonal conflicts, and cognitive changes such as memory problems and reduced attention. The phenomenon, sometimes called winter over syndrome, observed in Antarctic personnel during the long isolation of the polar winter, exhibits many of the psychological patterns that might emerge during long-duration space missions. Several factors make space travel particularly challenging psychologically. First is the extreme confinement. Space vehicles are necessarily limited in size, restricting movement and privacy. The International Space Station, with a habitable volume of approximately 388 cubic meters shared among 6 crew members, is positively spacious compared to proposed interplanetary spacecraft, where volume and mass constraints would likely be even more severe. Second is the sensory monotony of the space environment. The lack of variation in surroundings, the absence of natural features like weather, vegetation, or animal life, and the constrained range of textures, sounds, and smells all contribute to a sensory deprivation that humans find stressful over extended periods. The consistent artificial lighting and regulated temperature lack the natural variations that help maintain normal circadian rhythms and psychological well-being. Third is the combination of isolation and risk. Space travelers must cope not only with separation from family, friends, and the broader human community, but also with the knowledge that they face continuous danger in an environment immediately lethal without technological protection. This combination produces chronic stress that can degrade psychological performance and interpersonal dynamics over time. For missions beyond Mars, communication delays would eliminate real-time conversation with Earth, amplifying the sense of isolation. A message to Saturn would take over an hour to receive a response, while interstellar distances would stretch communication delays to years. Crews would need to function with complete psychological autonomy, resolving conflicts and maintaining mental health without external support or intervention. The duration of potentially feasible interstellar missions, measured in decades or generations, exceeds any space mission yet attempted by orders of magnitude. The longest continuous human presence in space has been Russian cosmonaut Valery Polyakov's 438 days aboard the Mir space station. The psychological effects of confinement and isolation lasting decades cannot be fully predicted from current experience, but would likely present challenges beyond anything we have studied to date. Various approaches have been proposed to address these psychological challenges. Crew selection represents a first line of defense, identifying individuals with psychological profiles suited to extended isolation and confinement. Characteristics like emotional stability, intrinsic motivation, and skill with conflict resolution appear particularly important for long-duration missions. Habitat design can incorporate features that support psychological health, including private spaces, variable lighting that mimics Earth's day-night cycle, and internal architecture that reduces the sense of confinement. Virtual reality or other advanced entertainment systems might help alleviate monotony and provide the sensation of being in varied environments despite physical constraints. Crew composition and social structure would be crucial for extended missions. Some research suggests that mixed-gender crews perform better on long-duration missions than single-gender groups, showing more cohesive social interaction and reduced conflict. Cultural diversity provides both benefits, like different perspectives on problem-solving, and challenges, such as communication difficulties and different behavioral norms. For truly long-duration missions, particularly generation ships where inhabitants would live their entire lives aboard, social structures would need to support not just mission functions, but the full range of human development and social needs. This might require populations large enough to maintain genetic diversity and social complexity, estimated at a minimum of several hundred individuals, and potentially thousands for truly long-term viability. These biological and psychological limitations do not necessarily represent absolute barriers to deep space travel. Various technological or biological solutions might potentially address many of them, though such solutions remain largely theoretical at present. Artificial gravity through rotation could maintain musculoskeletal health. Advanced radiation shielding or active protection systems might reduce exposure to cosmic rays. Closed ecological systems, once perfected, could sustain human life indefinitely. More speculative approaches involve direct modification of human biology to better suit the space environment. Genetic engineering or other biotechnologies might potentially create humans more resistant to radiation, better adapted to microgravity, or with reduced resource requirements. Such modifications raise profound ethical questions, but might represent the most direct solution to the fundamental mismatch between Earth-evolved biology and the conditions of space. Suspended animation or hibernation technologies, if developed, could address both biological and psychological challenges by reducing metabolic activity during transit. This would decrease lifetime radiation exposure, resource consumption, and the psychological burden of conscious existence during monotonous journey phases. While human hibernation remains firmly in the realm of science fiction, research into torpor states induced by hydrogen sulfide or other compounds has shown promising results in small mammals. An even more radical approach would be to send only human genetic material or synthetic genetic codes, along with artificial wombs or other reproductive technology, to be activated only upon reaching the destination. This would eliminate the challenges of sustaining adult humans during transit, but raises complex ethical issues about creating humans in isolation from the broader human community and without prior consent. For all these potential solutions, significant gaps remain between current capabilities and what would be required for successful interplanetary or interstellar missions. The human organism, exquisitely adapted for life on Earth, faces fundamental challenges in the space environment that cannot be easily dismissed or overcome with foreseeable technology. However, the history of human adaptation suggests caution in declaring absolute biological limitations. Humans have successfully inhabited environments from Arctic tundra to Amazonian rainforest, from high-altitude mountains to coastal deserts, adapting through both technology and biology to conditions far outside our original evolutionary context. Space represents a more extreme case, but follows the same pattern of extending human presence beyond our original habitat. The biological and psychological challenges of deep space travel are formidable, but not necessarily insurmountable, given sufficient time, research, and technological development. They do, however, suggest that human expansion into the cosmos may follow a more gradual and complicated path than often depicted in popular imagination. The journey outward will be constrained not just by the physics of distance and propulsion, but by the inherent limitations of bodies and minds shaped by evolution on a single small planet circling an ordinary star. As we contemplate how far humanity might travel in space, we must consider not just the vehicles that would carry us, but the fundamental adaptability of our biology and psychology to the extreme environments we would encounter. The ultimate horizons of human space travel may be determined not by the laws of physics or the capabilities of our technology, but by the extent to which we can adapt ourselves, either through technology or biology, to exist beyond the planetary cradle in which we evolved. As we contemplate the immense challenges of venturing beyond our solar system, we must ask what might await us among the stars. What discoveries might justify the extraordinary effort required to reach even the nearest stellar neighbors? What might we find that would transform our understanding of the universe and our place within it? The answer lies in the astonishing diversity of worlds that populate our galaxy, many potentially harboring conditions conducive to life unlike anything in our home system. Our understanding of what exists beyond our solar system has undergone a revolution in recent decades. When the first human beings ventured into space in the mid-20th century, we had no confirmed evidence of planets orbiting other stars. The existence of exoplanets, while considered likely by many astronomers, remained theoretical. Today, we have confirmed the existence of over 5,000 exoplanets, with thousands more candidates awaiting verification, fundamentally transforming our perspective on planetary systems. This revolution began in earnest in 1995 with the discovery of 51 Pegasi b, a Jupiter-sized planet orbiting surprisingly close to its star. Since then, multiple detection methods have revealed planets of astonishing diversity, from gas giants larger than Jupiter to rocky worlds smaller than Earth, orbiting stars of almost every type. We now understand that planets are the rule rather than the exception around stars, with most harboring multiple worlds. The Kepler Space Telescope, launched in 2009, provided a statistical breakthrough by monitoring approximately 150,000 stars continuously for tiny dips in brightness caused by transiting planets. Its findings suggest that, on average, every star in our galaxy hosts at least one planet, with small, rocky planets being the most common type. Our Milky Way galaxy alone may contain hundreds of billions of planets, tens of billions of which may be approximately Earth-sized and orbiting in their stars' habitable zones. This abundance of potentially habitable worlds transforms our thinking about what might await us beyond our solar system. The nearest star system to Earth, Alpha Centauri, consists of 3 stars, Alpha Centauri A and B, which orbit each other as a binary pair, and Proxima Centauri, a small red dwarf star orbiting the pair at a greater distance. In 2016, astronomers announced the discovery of Proxima Centauri b, an Earth-sized planet orbiting in the star's habitable zone, just 4.2 light-years from our Sun. Since then, additional planets have been discovered or proposed in the Alpha Centauri system, including a possible second planet around Proxima Centauri and a Neptune-sized world orbiting Alpha Centauri A. These findings suggest that our nearest stellar neighbors may host complex planetary systems with potential for habitability, making them compelling destinations for future exploration. Despite the formidable challenges of interstellar travel, beyond Alpha Centauri, numerous nearby stars host confirmed exoplanets of interest. The TRAPPIST-1 system, 39 light-years away, contains 7 Earth-sized planets orbiting a small red dwarf star, with several potentially in the habitable zone. Tau Ceti, just 12 light-years distant, appears to host at least 4 planets, including 2 that may be super-Earths in the habitable zone. These and many other nearby systems represent potential targets for interstellar missions, should they ever become technically feasible. What conditions might we find on these distant worlds? The diversity of exoplanets discovered to date suggests environments far more varied than those within our solar system. Some gas giants orbit so close to their stars that their atmospheres reach temperatures of thousands of degrees, hot enough to vaporize metals like iron and titanium. Others orbit at distances similar to Jupiter or beyond, with frigid upper atmospheres but potentially warmer conditions deeper within their gaseous envelopes. Super-Earths, a category not represented in our solar system, are planets with masses between Earth's and Neptune's. These worlds might be scaled-up versions of Earth, with similar composition but stronger gravity, or mini-Neptunes, with substantial envelopes of hydrogen and helium surrounding rocky or icy cores. The boundary between these types appears to fall around 1.7 Earth radii, though factors like proximity to the star and formation history also influence a planet's composition. Rocky planets similar in size to Earth represent the most intriguing targets for potential habitability as we understand it. These worlds might have diverse surface conditions depending on their distance from their star, atmospheric composition, and geological activity. Some could be Venus-like, with thick carbon dioxide atmospheres creating runaway greenhouse effects and surface temperatures hot enough to melt lead. Others might be Mars-like, with thin atmospheres and cold, desert-like conditions. Still, others could be water worlds, covered entirely by deep global oceans with no exposed land. Most exciting are those rocky planets orbiting within their stars' habitable zones, where temperatures potentially allow liquid water to exist on the surface. This zone, sometimes called the Goldilocks region, represents the range of distances from a star where a planet with an Earth-like atmosphere would be neither too hot for water to remain liquid, nor too cold for it to be permanently frozen. The precise boundaries depend on factors like the star's brightness, the planet's atmospheric composition, and its reflectivity or albedo. However, orbiting in the habitable zone does not guarantee conditions suitable for life. Venus orbits at the inner edge of our Sun's habitable zone, yet its thick carbon dioxide atmosphere creates surface conditions incompatible with life as we know it. Mars orbits near the outer edge of the habitable zone, yet its thin atmosphere and lack of magnetic field protection have resulted in cold, arid conditions where liquid water appears only transiently, if at all. A truly Earth-like exoplanet would need not just the right orbital distance, but a suitable atmosphere, active geology, a magnetic field to shield against stellar radiation, and stable orbital parameters, among other factors. Whether such ideal conditions exist together commonly or rarely remains one of the greatest unanswered questions in astronomy, one that future telescopes like the James Webb may help address by characterizing exoplanet atmospheres in unprecedented detail. Planets orbiting red dwarf stars present particular interest and challenges for habitability. These stars, smaller and cooler than our Sun, are the most common type in the galaxy, comprising approximately 75% of all stars. Their lower mass and energy output mean that their habitable zones lie much closer to the star than in our solar system, typically at distances comparable to or less than that of Mercury from our Sun. This proximity creates challenges for life. Planets orbiting so close to their stars become tidally locked, with one hemisphere perpetually facing the star, while the other remains in darkness. This could create extreme temperature differences between the day and night sides, potentially unstable for global climate. Additionally, red dwarf stars are more prone to powerful flares and high-energy radiation, which could strip away planetary atmospheres over time and bombard surfaces with radiation harmful to life as we know it. Yet these challenges may not be insurmountable. Climate models suggest that an atmosphere thick enough to transport heat from the day side to the night side could moderate temperature extremes on tidally locked planets. Magnetic fields, if present, might provide some protection against stellar radiation. Indeed, the prevalence of red dwarf stars means that if even a small percentage of their planets overcame these challenges, they might represent the most common habitable environments in the universe. Beyond considering planetary conditions in their current state, we must also consider their evolution over geological and astronomical timescales. The concept of a continuously habitable zone acknowledges that stars gradually increase in brightness over their main sequence lifetimes. This means that a planet initially too cold might enter the habitable zone as its star ages, while one initially habitable might eventually become too hot. Like Earth, will in approximately 1 billion years, as the Sun continues to brighten. Planets that maintain habitable conditions for billions of years, as Earth has done, may be relatively rare. Such long-term stability requires a combination of factors including a stable star, a nearly circular orbit, protection from excessive asteroid or comet impacts, and geological processes that regulate atmospheric composition through time. Finding such planets would be of particular interest for the potential development of complex life, which on Earth required billions of years of relatively stable conditions. What forms might life take on habitable exoplanets? While we cannot know with certainty until we detect and study such life directly, we can make educated speculations based on our understanding of environmental constraints and the chemical foundations of life on Earth. Carbon-based biochemistry seems likely on other worlds due to carbon's unparalleled ability to form complex, stable molecules with diverse properties. Water as a solvent also offers advantages, with its unusual properties including expanded volume when frozen, high heat capacity, and ability to dissolve a wide range of compounds. However, alternative biochemistries cannot be ruled out entirely. Silicon might substitute for carbon in some environments, while ammonia or methane could potentially serve as solvents at temperatures too cold for liquid water. The specific forms of alien life would depend heavily on local conditions. On planets with higher gravity than Earth, organisms might evolve more compact, muscular bodies. Those with denser atmospheres might develop flight more easily, or face less need for rigid skeletons due to greater buoyancy. Planets with less intense sunlight might evolve life forms with different photosynthetic pigments, optimized for different wavelengths of light, potentially giving their vegetation colors other than green. On tidally locked planets orbiting red dwarf stars, the eternal day side might host life adapted to constant light, but with strong defense mechanisms against radiation damage. The night side might develop ecosystems based on geothermal energy or organisms that migrate between the permanent twilight zones. The boundary between day and night sides, where temperature gradients would be steep, might host particularly dynamic and diverse ecosystems. Perhaps most exciting is the possibility of discovering biospheres entirely unlike Earth's. Life on our planet shares a common ancestry, with all organisms using the same genetic code and core biochemical pathways. Truly independent origins of life might have explored evolutionary pathways that never developed on Earth, potentially leading to fundamentally different approaches to metabolism, reproduction, or information storage. The detection of such alien biospheres represents one of the greatest scientific prizes awaiting humanity beyond our solar system. Current and planned astronomical observations can detect potential biosignatures, such as oxygen and methane coexisting in an atmosphere, which on Earth results from biological activity. However, definitive confirmation of life would likely require detailed in situ investigation, potentially including sample return, that only physical missions to these distant worlds could provide. Beyond the search for life, exoplanets offer windows into planetary formation and evolution that could help us better understand our own solar system. The surprising diversity of planetary systems discovered to date challenges many of our previous assumptions about how planets form and organize themselves. Hot Jupiters orbiting close to their stars, super-Earths with no analog in our system, and tightly packed multi-planet systems defy the orderly pattern we observe from Mercury to Neptune. Studying these diverse systems helps refine our models of planetary formation, potentially revealing whether our solar system represents a common or unusual arrangement. This knowledge has practical implications for understanding Earth's history and future, including the frequency of major impacts and the long-term stability of planetary orbits, both of which can affect habitability. Unusual astronomical phenomena also await discovery beyond our solar system. Binary star systems, where two stars orbit each other, create complex gravitational environments that may allow for exotic planetary orbits, including circumbinary planets that orbit both stars simultaneously. The dynamics of such systems differ significantly from our single star experience, potentially creating seasonal patterns and climate variations unlike anything on Earth. Giant exoplanets, particularly young ones still radiating heat from their formation, might host complex moon systems with conditions suitable for life. Jupiter's moon Europa harbors a subsurface ocean that might support life, despite Jupiter itself being uninhabitable. Similarly, exomoons orbiting giant planets in habitable zones might represent environments as suitable for life as planets themselves, potentially multiplying the number of habitable worlds. Brown dwarfs, objects intermediate between giant planets and small stars, represent another interesting target for exploration. Too small to sustain hydrogen fusion like true stars, they nevertheless emit infrared radiation from the slow release of gravitational energy. Planets orbiting brown dwarfs would receive minimal visible light but potentially adequate infrared heating to maintain habitable conditions, enabling exotic biospheres based on infrared rather than visible radiation. Beyond examining individual worlds, reaching nearby star systems would allow us to study interstellar space itself in unprecedented detail. The boundary between our Sun's influence and true interstellar space, known as the heliopause, represents a frontier that our Voyager spacecraft have only recently crossed. The properties of the interstellar medium, including its composition, magnetic fields, and particle densities remain imperfectly understood due to the challenges of remote observation. The ultimate astronomical prize beyond our solar system would be the discovery of technological signatures indicating the presence of other civilizations. While current efforts to detect such signatures rely on astronomical observations, including radio telescopes searching for artificial signals, physical exploration of nearby star systems would allow for more definitive searches. These searches might include detection of atmospheric modification beyond natural processes, artificial structures visible from space, or electromagnetic emissions consistent with technological activity. While the probability of finding such signatures remains unknown given our complete lack of data on the frequency of technological civilizations, the scientific and philosophical impact of such a discovery would be incalculable, fundamentally transforming our understanding of our place in the cosmos. Even without discovering other technological species, interstellar exploration would provide unprecedented insights into the distribution and nature of life in the universe. Are habitable planets common or rare? Does life emerge readily whenever conditions permit, or does it require exceptional circumstances? How similar or different are independently evolved biospheres? These questions touch on some of the most profound aspects of our existence, potentially revealing whether life is a cosmic accident or an expected outcome of physical and chemical processes. The destinations potentially reachable through interstellar travel, even limited to the nearest tens of light years, offer scientific prizes worthy of the extraordinary effort required to reach them. From characterizing exotic planetary environments to searching for novel forms of life, from testing planetary formation theories to hunting for signs of other civilizations. These nearby star systems represent a frontier of discovery comparable to the greatest explorations in Earth's history. Yet we must also recognize that the most transformative discoveries may be those we cannot currently anticipate. When Galileo first turned his telescope toward Jupiter in 1610, he discovered the planet's 4 largest moons, a finding that helped validate the Copernican model of the solar system and fundamentally changed humanity's understanding of our place in the cosmos. Similarly, our first detailed observations of nearby planetary systems, whether through advanced telescopes or eventual physical exploration, may yield discoveries that transform our perspective in ways we cannot currently imagine. As we contemplate what we might find out there among the stars, we are constantly reminded of how much remains unknown despite our technological progress. The discovery of exoplanets themselves came surprisingly late in our astronomical history, with the first confirmations occurring only in the 1990s. What other aspects of nearby star systems might await discovery, hiding in plain sight until we develop the right observational techniques or theoretical frameworks to recognize them? This sense of wonder and possibility, the knowledge that transformative discoveries await beyond our solar system, provides perhaps the strongest motivation for developing the capabilities for interstellar exploration. Despite the enormous challenges involved, the potential scientific return extends beyond specific findings to a broader, more profound understanding of the universe and our place within it, a perspective that might fundamentally reshape human civilization and our long-term trajectory as a species. As we have ventured through the possibilities of human exploration within our solar system and to nearby stars, we have confronted formidable but potentially surmountable obstacles. Now we turn our gaze to the ultimate horizon, the edge of the observable universe itself, where we encounter limits that may be truly fundamental, barriers defined not by our technological capabilities but by the very nature of physics and cosmology. The observable universe represents all that we can potentially see or interact with, a sphere of space-time, approximately 93 billion light-years in diameter centered on Earth. This vast expanse contains an estimated 2 trillion galaxies, each housing hundreds of billions of stars, together with their planets, nebulae, black holes, and other cosmic structures. It is a realm of almost unimaginable scale and diversity, yet it represents only a fraction of what may exist beyond our cosmological horizon. The concept of the observable universe itself requires some reflection. We cannot see the universe as it exists today. Rather, we see objects as they were when the light now reaching us began its journey. When we observe a galaxy 10 billion light-years away, we see it not as it is now, but as it was 10 billion years ago, when the universe was less than 4 billion years old. This means our view of the distant universe is also a look back in time, revealing earlier epochs in cosmic history rather than the current state of faraway regions. Further complicating our understanding is the fact that many of the most distant objects we can observe no longer exist in the forms we see them. Ancient galaxies may have merged with others. Stars we observe may have long since exploded as supernovae, and the exact regions of space they occupied have been carried far away by cosmic expansion. Our observable universe is thus partly a cosmic fossil record, preserving images of objects and arrangements that have long since transformed. But why, you might wonder, is the observable universe 93 billion light-years across, when the universe is only 13.8 billion years old? Shouldn't the most distant objects we can see be at most 13.8 billion light-years away, the distance light could travel since the Big Bang? The answer lies in the expansion of space itself. While nothing can travel through space faster than light, space itself can expand more rapidly, carrying distant galaxies away from us at apparent speeds exceeding the speed of light. This expansion has profound implications for our discussion of how far humanity might travel. Unlike the challenges of propulsion, radiation, or life support that we explored earlier, the expansion of the universe creates barriers that no foreseeable technology could overcome, defining absolute limits to our potential reach into the cosmos. To understand these limits, we must first grasp how cosmic expansion shapes our universe. In the early 20th century, astronomers including Edwin Hubble discovered that distant galaxies appear to be moving away from us, with more distant galaxies receding faster than nearer ones. This observation led to the formulation of Hubble's law, which states that a galaxy's recession velocity is proportional to its distance from us, described by a value called the Hubble constant. This relationship arises not because we occupy a special position in the universe, but because space itself is expanding everywhere. Imagine a loaf of raisin bread rising in an oven. As the dough expands, each raisin moves away from every other raisin, with more distant pairs separating faster than nearby ones. Similarly, in our expanding universe, every galaxy observes all other galaxies receding, with more distant ones moving away more rapidly. The current value of the Hubble constant indicates that for every megaparsec, approximately 3.3 million light-years, a galaxy recedes from us at about 73 kilometers per second. This means that sufficiently distant galaxies, roughly 14 billion light-years away under current conditions, recede faster than the speed of light. Beyond this distance lies what cosmologists call the cosmic event horizon. The cosmic event horizon represents a fundamental barrier to both communication and travel. Light emitted today from objects beyond this horizon will never reach us, as the expansion of intervening space outpaces the light's journey toward Earth. Similarly, we could never reach these regions regardless of our technology, as they move away faster than any signal or spacecraft could travel through space. This horizon is not static but changes with cosmic time. In the early universe, the Hubble constant was much larger, meaning that the observable universe was much smaller. As the universe ages, the Hubble constant decreases, allowing us to observe more distant regions. However, the acceleration of cosmic expansion, discovered in the late 1990s, suggests that this growth of the observable universe will eventually cease, establishing a finite volume of space that will ever be accessible to us. Given these cosmological realities, let us consider the actual distances involved and what they mean for potential human expansion. Our Milky Way galaxy spans about 100,000 light-years. The Local Group, the collection of galaxies gravitationally bound to the Milky Way, extends to about 10 million light-years. The Virgo supercluster, a larger structure containing the Local Group among many other galaxy clusters, spans roughly 110 million light-years. These scales, while vast compared to our current exploration capabilities, lie well within the cosmic event horizon. With sufficiently advanced technology and the expanses of time we have discussed in previous chapters, humanity, or its descendants, could potentially explore much of the Local Group, assuming solutions to the propulsion, lifespan, and communication challenges we have identified. However, the Virgo supercluster itself is being pulled toward an even larger structure called the Great Attractor, which in turn forms part of the Laniakea supercluster, spanning about 500 million light-years. Beyond lie even larger structures, filaments and walls of galaxies surrounding vast cosmic voids, extending to the limits of the observable universe. Most of these more distant structures lie beyond what we might call the practical horizon for human expansion, even assuming the most optimistic technological developments over cosmic timescales. This practical horizon is determined not just by the physical limits imposed by cosmic expansion, but by the timescales involved. Even traveling at 99% of light speed, reaching galaxies billions of light years away would require billions of years, timeframes comparable to the remaining lifespan of the Sun and other main sequence stars. Moreover, the accelerating expansion of the universe means that galaxies currently visible, but sufficiently distant, are receding from us at ever-increasing speeds. In the far future, perhaps 100 billion years from now, most galaxies currently visible will have disappeared beyond our cosmic event horizon, leaving only the local group and perhaps a few nearby galaxy clusters as the sum total of the observable universe for any future observers. This accelerating expansion results from dark energy, a mysterious component of the universe that acts as a kind of anti-gravity, pushing space apart rather than pulling it together. Current measurements indicate that dark energy comprises about 68% of the mass energy density of the universe, with dark matter accounting for another 27%, and ordinary matter, the stuff of stars, planets, and living things, making up less than 5%. The nature of dark energy remains one of the greatest unsolved problems in physics. It may be a cosmological constant, an inherent property of space itself, as suggested by Einstein's general theory of relativity. Alternatively, it could be a dynamic field that varies over time and space, or perhaps an indication that our understanding of gravity breaks down at cosmic scales. Whatever its nature, dark energy appears to determine the ultimate fate of our universe and, by extension, the absolute limits of potential human expansion. If dark energy maintains its current properties, the universe will continue expanding at an ever-accelerating rate. Distant galaxies will recede beyond our cosmic event horizon, never to be seen again. Over much longer timescales, even nearby galaxy clusters will separate, and eventually even individual galaxies will dissipate as stars are flung away from each other. In the extreme far future, perhaps 100 trillion years hence, the observable universe for any hypothetical observer would consist of just a single aging galaxy. This scenario, sometimes called the cosmic heat, death, or big freeze, represents one possible ultimate fate for the universe, based on current observations. Alternative possibilities, such as a big crunch where expansion eventually reverses into contraction, or a big rip where dark energy strengthens until it tears apart even atoms, appear less likely given current measurements, though our understanding continues to evolve with new data. What does this cosmological perspective mean for the ultimate limits of human travel? It suggests that even with perfect technology and unlimited time, there exist regions of the universe that we simply cannot reach, places beyond an unbridgeable cosmic horizon. The universe, despite its vastness, presents not just practical limitations but absolute ones, barriers that transcend our technological capabilities and arise from the fundamental nature of space-time itself. This realization might seem disheartening at first. The universe contains an estimated 1 billion trillion stars, with their attendant planets, moons, and other celestial bodies. Yet the overwhelming majority will remain forever beyond our reach, no matter how advanced our civilization might become. Even the light from many of these distant objects will eventually cease to reach us, as cosmic expansion accelerates them beyond our horizon. Yet this limitation should be considered in context. The local group, which will remain accessible even in the far future as gravitationally bound structures resist cosmic expansion, contains at least 54 galaxies, including our Milky Way, the Andromeda Galaxy, and the Triangulum Galaxy, along with numerous dwarf galaxies. Together, these contain trillions of stars and potentially habitable planets, a domain so vast that exploring even a fraction would require timescales far beyond human history to date. The structure of our local group itself is fascinating and worth understanding as we contemplate the limits of potential exploration. At its center lie the two largest spiral galaxies, the Milky Way and Andromeda, each spanning over 100,000 light-years in diameter. Orbiting these behemoths are numerous satellite galaxies, much like moons orbiting planets. Our Milky Way has at least 50 known satellite galaxies, with the Large and Small Magellanic Clouds being the most visible from Earth's southern hemisphere. These satellite galaxies are diverse in structure and composition. Some are dwarf ellipticals, containing mostly older stars, with little ongoing star formation. Others are dwarf irregulars with more gas and dust, actively forming new stars. Several, like the Sagittarius dwarf spheroidal galaxy, are being gravitationally torn apart as they orbit the Milky Way, leaving streams of stars that wrap around our galaxy like cosmic ribbons. The spaces between the major galaxies of the local group are not empty, but contain immense clouds of hydrogen gas, some of which form bridges and filaments connecting the galaxies. These structures, along with the diffuse halos of dark matter surrounding each galaxy, bind the local group into a coherent, gravitationally bound structure that will resist the expanding force of dark energy indefinitely. Consider that humans have directly explored only a minute fraction of our own solar system, with crewed missions limited to the Moon and robotic explorers having visited all major planets, but only a handful of smaller bodies among the millions that orbit our Sun. Our exploration of even the Milky Way has been limited to astronomical observations, with our most distant spacecraft having barely left the solar neighborhood. Given this perspective, the cosmic event horizon represents a theoretical limit so distant from our current capabilities that it has little practical relevance to human ambitions in the foreseeable future. Even if we restrict our consideration to what lies within this ultimate horizon, the potential domain for human exploration and potentially settlement remains almost unimaginably vast. Nevertheless, contemplating these cosmic limits provides important context for our earlier discussions. When we consider the challenges of interplanetary travel within our solar system, or the even greater difficulties of reaching nearby stars, we should remember that these represent the earliest, most accessible frontiers of a cosmic domain that extends far beyond, though not infinitely so. The cosmological perspective also offers insights into the time constraints on our long-term ambitions. The universe evolves over cosmological timescales, with structures forming, stars being born and dying, and galaxies interacting and merging. If humanity or its successors persist for millions or billions of years, they would witness and perhaps participate in these cosmic processes. For example, astronomical projections indicate that the Milky Way and Andromeda galaxies will collide and begin merging in approximately 4.5 billion years. Around the same time, our Sun is expected to leave the main sequence and expand into a red giant. This merger would transform our local galactic environment, potentially disrupting planetary systems but also triggering new star formation and creating new opportunities for life. This future collision will be a spectacular, drawn-out event lasting hundreds of millions of years. The first approach will create gravitational distortions in both galaxies, drawing out long tidal tails of stars, gas, and dust. As the galaxies pass through each other, their spiral structures will be disrupted, creating chaotic flows of stellar material and triggering bursts of new star formation as gas clouds collide and compress. Despite the apocalyptic sound of a galactic collision, individual stars are so widely spaced that direct stellar collisions would be extremely rare. Our Sun would almost certainly survive the initial passes, though it might be flung into a different orbit around the new galactic center. However, the distribution of gas and dust would be fundamentally altered, potentially affecting the formation of new stellar and planetary systems. After several passes over hundreds of millions of years, the two spiral galaxies would settle into a single massive elliptical galaxy, sometimes called Milkomeda by astronomers. This new galaxy would contain all the stars from both predecessors, but would lose the beautiful spiral structure we see today. Star formation would gradually decline as the available gas becomes depleted, leaving an increasingly elderly stellar population dominated by red dwarf stars and stellar remnants. Any advanced civilization existing during this transition would have both challenges and opportunities. The changing gravitational environment might threaten established planetary systems, requiring technological interventions to maintain habitable conditions. Conversely, the collision would create new regions of star formation, potentially giving rise to fresh solar systems with resources to sustain expansion. On even longer timescales, star formation throughout the universe will gradually slow as gas and dust are converted into stars, and eventually locked in stellar remnants like white dwarfs, neutron stars, and black holes. Perhaps 100 trillion years from now, the last sun-like stars will exhaust their nuclear fuel, leaving a universe populated primarily by red dwarf stars that can burn for trillions of years, along with the cold remnants of long-dead larger stars. Eventually, after unimaginable eons, even these red dwarfs will exhaust their fuel, leaving a cold, dark universe populated by white dwarfs, neutron stars, and black holes. These stellar remnants will gradually decay through various processes, with white dwarfs cooling to black dwarfs, neutron stars potentially collapsing to black holes, and even black holes themselves eventually evaporating through Hawking radiation over truly astronomical timescales, perhaps reaching 10 to the power of 100 years. This far future cosmology places our earlier discussions of human space travel in a broader temporal context, just as the cosmic event horizon places them in a spatial context. The universe not only has regions that will forever remain inaccessible to us, but also a finite window of habitability during which stars shine and complex physical structures can exist. The study of these ultimate limits falls under the domain of physical eschatology, the branch of physics concerned with how the universe and its structures will evolve in the far future. Current understanding suggests that while the universe itself may persist indefinitely, its capacity to support complex structures like galaxies, stars, planets, and living things will not. Given enough time, entropy increases to the point where organized complexity becomes impossible. This progression toward cosmic heat death would unfold across unimaginable timescales. Following the Stelliferous era, our current cosmic epoch, dominated by star formation and active galaxies, the universe would enter the degenerate era, lasting from approximately 100 trillion to 1 quintillion years from now. During this immensely long period, conventional star formation would cease, leaving the universe populated primarily by stellar remnants, white dwarfs, neutron stars, and black holes. White dwarfs, the remnants of sun-like stars, would gradually cool into black dwarfs, inert spheres of carbon and oxygen. These objects, while cold and dark, would still retain complex internal structure. Neutron stars would similarly cool, losing their luminosity but maintaining their incredible density and strong magnetic fields. Black holes of various sizes, from stellar mass to supermassive, would dominate the dynamics of the aging galaxies, occasionally consuming other remnants that venture too close. On even longer timescales, proton decay, a process currently unconfirmed but predicted by some theories of particle physics, could gradually erode even these stellar remnants. Over periods approaching 100 quintillion years, protons and neutrons might spontaneously convert to lighter particles, causing even the most stable structures to slowly dissolve into radiation. Black holes would become the last complex structures in the universe. Yet even black holes are not eternal. Through the process of Hawking radiation, black holes gradually emit particles and lose mass. This process accelerates as they shrink, leading to an eventual evaporation in a final burst of elementary particles. The larger the black hole, the longer this process takes. Supermassive black holes might persist for up to 1 Google years, or 10 raised to the power of 100, an almost incomprehensible time span. After the last black hole evaporates, the universe would enter the dark era, a state of almost perfect entropy, where matter exists only as dispersed fundamental particles separated by ever-increasing distances due to cosmic expansion. In this final state, no complex structures would exist, and no work could be performed. The universe would reach a state of maximum disorder, with temperatures approaching absolute zero everywhere except for the occasional random quantum fluctuations. For any civilization aspiring to truly cosmic longevity, these considerations would eventually become relevant. A sufficiently advanced society might need to manage resources on galactic scales, perhaps moving stars to maintain stable clusters resistant to cosmic expansion, harvesting energy from black holes, or developing ways to utilize dark energy itself. Such activities lie far beyond our current technological horizon, but represent theoretical possibilities within the laws of physics as we understand them. Even with such godlike capabilities, however, the cosmic event horizon would remain an absolute limit. No civilization, regardless of its advancement, could reach or even communicate with regions beyond this horizon. In an accelerating universe, each civilization or species remains constrained to an ever more isolated pocket of space-time, eventually losing contact with all but its immediate galactic neighbors. This cosmological isolation has philosophical implications about the nature and purpose of expansion through space. If we cannot reach the entire universe, if indeed most of it lies forever beyond our grasp, what meaning does cosmic expansion have? Perhaps the answer lies not in the breadth of territory covered, but in the diversity of environments explored and the depth of understanding gained about the fundamental nature of reality. From this perspective, the 93 billion light-year diameter of our observable universe, while representing an absolute limit to potential expansion, contains such diversity and complexity that it might as well be infinite for practical purposes. The number of potentially habitable planets within the local group alone exceeds by orders of magnitude what humanity could realistically explore or settle even over millions of years with foreseeable technology. Consider also that cosmic expansion affects only the largest scales of the universe. Within gravitationally bound structures like galaxies and galaxy clusters, the mutual gravitational attraction overcomes the cosmic expansion, allowing these structures to remain intact and even condense further over time. The Milky Way will not be torn apart by cosmic expansion, nor will the local group of galaxies to which it belongs. This means that even in the far future, when distant galaxies have receded beyond the cosmic horizon, a vast domain would remain potentially accessible, comprising trillions of star systems across dozens of galaxies. While this represents a tiny fraction of the current observable universe, it exceeds by almost unimaginable factors the scale of human civilization today, confined as we are to a single planet, orbiting an ordinary star in the outer regions of one spiral arm of our galaxy. The cosmic event horizon thus represents a theoretical absolute limit to potential human expansion, but one so distant in both space and time from our current position that it has little practical relevance to near or medium-term ambitions for space exploration and settlement. Like the heat death of the universe itself, it represents an ultimate boundary condition for the most ambitious possible projections of human or post-human civilization, but not a constraint on what might be achieved in the coming centuries or millennia. For our purposes in contemplating how far humanity might travel in space, we might usefully distinguish between several horizons of increasing distance and difficulty. The first is the practical horizon of near-term human exploration, which currently extends only to the Moon and perhaps Mars in the coming decades. The second is the technological horizon, representing where we might reach with foreseeable advances in propulsion, life support, and related fields, perhaps encompassing the entire solar system and potentially nearby star systems within a few light years. Beyond lies what we might call the theoretical horizon, representing destinations that could be reached only with technologies that remain speculative but do not violate known physical laws, such as fusion drives, antimatter rockets, or generation ships. This horizon might extend to nearby stellar neighborhoods, within perhaps 100 light years, encompassing thousands of star systems. Further still is the post-human horizon, where we consider what might be possible for our distant descendants or successors who may have transcended biological limitations through technological or evolutionary means. This horizon could potentially encompass significant portions of the Milky Way galaxy over timeframes of millions of years. This post-human horizon deserves further exploration. Over evolutionary timescales, humanity itself might change substantially, either through natural selection in diverse environments or through deliberate genetic engineering. Adaptations to different gravity levels, radiation environments, or atmospheric compositions might create distinct branches of humanity, specialized for different cosmic habitats. More radical possibilities include technological integration that fundamentally changes what we consider human, neural interfaces, mind uploading to artificial substrates, or hybridization with artificial intelligence might create beings that retain human origins and values, but possess capabilities far beyond our current biological limitations. These post-human entities might operate on different timescales, potentially extending subjective lifespans indefinitely or experiencing time at vastly accelerated rates. Such beings would approach cosmic exploration very differently than we would. Concerns about radiation exposure, life support, or psychological effects of extended isolation might become irrelevant. The ability to exist in digital or synthetic forms could allow transmission of consciousness patterns at light speed between established receiver stations, enabling exploration without physical travel of the original consciousness. Alternatively, posthumans might design specialized physical forms optimized for specific exploration missions, essentially becoming living spacecraft. Even more exotic possibilities might include forms of distributed consciousness spanning multiple physical bodies or locations, collective intelligences integrating multiple individual minds, or entities existing primarily as patterns of information that can inhabit various physical substrates as needed. Such beings would experience the universe in ways we can barely imagine, potentially perceiving aspects of reality hidden to our biological senses and cognitive patterns. The potential exploration strategies of such posthuman entities might include patient observation over geological or astronomical timescales, something biological humans find challenging due to our short lifespans. They might see distant star systems with self-replicating probes, programmed to establish communication relays, build receiver stations for transmitted consciousness, or prepare environments for later colonization. Rather than conquering distance through speed, they might embrace the slow unfolding of cosmic processes, watching and influencing the evolution of planetary systems or even galaxies over billions of years. Finally, we reach the absolute horizon defined by cosmic expansion, beyond which no physical entity or signal could ever reach, regardless of technology or time available. This horizon encompasses much of the currently observable universe, but will gradually contract over cosmological timeframes as the expansion of space accelerates. The vastness contained within even the nearest of these horizons dwarfs our current exploration capabilities by factors that defy easy comprehension. The solar system alone contains hundreds of substantial bodies worthy of detailed study, from the major planets and their diverse moons to dwarf planets, large asteroids, and comets, distributed through a volume of space that would take current spacecraft years or decades to traverse. As we contemplate the edge of the observable universe and the limits it places on potential human expansion, we should remember that we have barely begun our journey into space. The cosmic horizons we have identified, from the practical to the absolute, define a series of expanding domains for exploration that could occupy our species for timeframes ranging from centuries to millions of years, each presenting new challenges and discoveries. The fact that we cannot reach everything, that portions of the universe will forever remain beyond our grasp, does not diminish the grandeur of what lies within our potential reach. Like an infinite library containing all possible books, the accessible universe presents more complexity, beauty, and wonder than we could exhaust in even the most ambitious projections of human or posthuman civilization. As we close this exploration of the cosmic horizon, we should remember that we observe the universe not just as potential travelers, but as conscious entities capable of understanding and appreciating its structure and evolution. Through astronomy, cosmology, and physics, we can study and comprehend regions of space and time that we may never physically reach, extending our mental grasp far beyond the limits of our physical presence. In this sense, the ultimate boundary for humanity may not be defined by how far we can travel, but by how much we can understand. The observable universe, with its billions of galaxies, trillions of stars, and uncountable worlds, offers not just destinations for physical exploration, but a vast laboratory for expanding our comprehension of the fundamental nature of reality itself. As we have explored the various horizons of potential human space travel, from the practical challenges of reaching nearby planets to the fundamental limits imposed by cosmic expansion, we have primarily considered physical travel, the movement of human bodies, or human-created vehicles through space. But perhaps the most profound question about how far we might travel lies in reconsidering what exactly constitutes we in this context. Could the human mind, or some extension or evolution of it, travel further than physical human bodies ever could? This question leads us into realms where science, philosophy, and speculative technology intersect. The concepts we will explore remain largely theoretical, with some verging on the speculative, yet they are grounded in fundamental questions about consciousness, information, and the potential for intelligence to take forms beyond the biological structures that currently host our minds. The relationship between mind and brain represents one of the most enduring questions in philosophy and science. Throughout most of human history, The mind was often considered something separate from the physical brain, perhaps a soul or spirit that inhabited the body, but maintained a separate existence. Modern neuroscience has revealed the intimate connection between brain processes and mental states, showing how changes to the physical brain through injury, drugs, or stimulation directly affect consciousness, personality, and cognition. This understanding has led to what philosophers call the materialist or physicalist view of mind, which holds that mental phenomena, including consciousness itself, arise from physical processes in the brain. According to this perspective, the particular patterns of neural activity, the information processing and storage capabilities of our brains give rise to our subjective experiences. If this view is correct, it opens the theoretical possibility that similar patterns could be created in different physical substrates, potentially allowing minds to exist outside of biological brains. Let us begin by considering the limits of physical travel that we have established in previous chapters. Even with theoretical technologies like fusion drives, antimatter propulsion, or light sails, the vast distances between stars impose daunting challenges. Interstellar journeys would take decades or centuries using any foreseeable technology, with travel to other galaxies requiring millennia or longer. The biological and psychological strains of such journeys on human bodies and minds would be extreme, potentially requiring generation ships, hibernation technologies, or other approaches that stretch our current capabilities. Yet information already travels much faster than physical objects can move. Radio waves and other electromagnetic signals propagate at the speed of light, approximately 300,000 kilometers per second, the ultimate speed limit in our universe according to Einstein's theory of relativity. We routinely communicate with spacecraft throughout our solar system using such signals, and we have detected radio emissions from distant objects billions of light years away. Consider how we already conduct remote exploration. The Mars rovers, from Sojourner to Perseverance, represent extensions of human curiosity and intelligence operating on another world. Human operators on Earth send commands and receive data, experiencing Mars indirectly through these robotic emissaries. The light speed delay of up to 20 minutes each way makes this a halting conversation, but it demonstrates a principle: we can explore without being physically present. This form of remote presence could be extended further as technology advances. Immersive virtual reality and advanced haptic interfaces might someday allow humans on Earth to experience distant environments as if they were there, guiding robots with increasingly subtle and intuitive controls. Such telepresence would still be limited by light speed delays, making real-time control impossible beyond lunar distances, but could provide experiences far richer than simply viewing images or data. For exploration within our solar system, such telepresence might represent an intermediate step between robotic missions and human physical presence. Operators on Earth could guide complex operations on Mars, the moons of Jupiter, or the surface of Venus, without facing the risks and life support challenges of sending human bodies. The experience would be delayed and mediated, but could potentially capture much of the cognitive and perceptual aspects of exploration. However, for interstellar distances, even this approach breaks down. The 4.3-year delay for signals from Alpha Centauri makes any meaningful telepresence impossible. This leads us to more speculative approaches, involving not just remote control of robots, but transferring or replicating consciousness itself. This suggests an alternative approach to cosmic exploration. What if, instead of sending human bodies across interstellar or intergalactic distances, we could somehow send human minds as information? The concept of mind uploading, the theoretical transfer or copying of a human consciousness into a computational substrate, offers a potential pathway for such information-based travel that would circumvent many of the biological limitations we have discussed. The basic premise of mind uploading rests on several assumptions, the most fundamental being that consciousness arises from physical processes in the brain and can, in principle, be replicated in other physical substrates. This view, sometimes called substrate independence, suggests that the essential qualities of mind do not depend on the specific biology of human brains, but on the patterns and processes that biology implements, patterns that could potentially be instantiated in other media. If this premise holds true, then a sufficiently detailed copy of a human brain, implementing all the relevant patterns of information processing, would generate a consciousness indistinguishable from the original. This uploaded mind could potentially exist inside a computer system, experiencing a simulated environment or interfacing with the physical world through robotic extensions. The technical challenges of achieving such uploading would be enormous. The human brain contains approximately 86 billion neurons, each forming thousands of connections with other neurons, creating a network of breathtaking complexity. Moreover, brain function involves not just the connections between neurons, but the precise timing of signals, the chemical environment, the role of glial cells once thought to be merely supportive, and likely many subtleties we have yet to discover. Current approaches to mapping the brain, such as the Human Connectome Project, have made progress in identifying the general architecture of neural connections, but remain far from the level of detail that would be required for a functional reproduction of an individual brain. Even the simplest worm, Caenorhabditis elegans, with just 302 neurons, has not been successfully simulated in complete detail despite its connectome being fully mapped. Various approaches to uploading have been proposed. Whole brain emulation would attempt to scan an existing brain at sufficient resolution to capture all relevant structures, then create a software model implementing the same functional architecture. This might be done destructively, examining thin slices of preserved brain tissue, or non-destructively using advanced imaging technologies that could map neural connections in a living brain. An alternative approach would be gradual replacement, where biological neurons are slowly substituted with artificial equivalents that perform the same functions within the network. In principle, this could maintain continuity of consciousness throughout the process, as the biological and artificial components would work together seamlessly during the transition. Both approaches remain hypothetical, with significant technical barriers to implementation. Beyond the challenges of creating the upload itself lies the question of what substrate would host it. Conventional computing architectures differ fundamentally from the parallel, analog, and contextual processing of biological brains. Specialized neuromorphic computing systems that more closely mimic brain architecture might be necessary, potentially using quantum computing, molecular computing, or other advanced technologies that exceed the capabilities of current silicon-based systems. For space exploration, the implications are profound. Rather than sending fragile biological bodies across interstellar distances, we might send relatively compact and durable robotic probes carrying uploaded human minds. These digital explorers would not need life support systems, would be immune to radiation damage to biological tissues, and could potentially exist for centuries or longer without the deterioration that affects biological systems. Communication would still be limited by light speed, with messages between stars taking years to transmit. However, the uploaded explorers would have subjective experiences of the journey and exploration without the biological constraints of aging, boredom, or psychological isolation that would affect physical human travelers. Their cognitive processes could potentially be accelerated beyond biological rates, making even centuries-long journeys subjectively manageable. Moreover, once established in a distant star system, an uploaded mind could make copies of itself to explore multiple planets simultaneously, or send further copies to more distant stars. This process of digital expansion could potentially spread human consciousness throughout a galaxy far more rapidly than biological colonization could achieve, limited primarily by the speed of the initial probes and the time required to establish receiver stations or manufacturing facilities at each destination. This concept of self-replicating machines carrying information, sometimes called von Neumann probes after mathematician John von Neumann, who first developed the theoretical basis for self-replicating automata, offers a compelling pathway for galactic exploration. Unlike biological reproduction, which is constrained to roughly generational timeframes, machine replication could potentially occur much more rapidly, allowing exponential expansion throughout the galaxy. Such expansion raises interesting questions about resource use and potential impact on astronomical environments. Unconstrained replication could theoretically lead to consumption of all available resources, a scenario sometimes called the grey goo problem when applied to nanotechnology. Any sustainable approach to cosmic expansion through self-replicating systems would need ethical constraints and careful resource management built into its fundamental programming. Various scientists have proposed different models for how such expansion might unfold. Mathematician and physicist Frank Tipler suggested what he called the Omega Point, where intelligence gradually spreads throughout the universe, eventually gaining control over cosmic processes themselves. Others, like physicist and computer scientist Ray Kurzweil, have predicted a technological singularity where artificial intelligence surpasses human capabilities, potentially leading to rapid expansion of superintelligence throughout accessible space. A more measured approach might involve carefully designed restraints on replication and resource use, preserving natural systems for study while establishing limited presence in each star system visited. The expansion would proceed more deliberately, with each new settlement or outpost established only after thorough exploration and consideration of potential impacts. This approach would spread more slowly, but might better preserve both human values and the natural diversity of cosmic environments. Let us consider a concrete example to illustrate this possibility. Imagine a self-replicating probe carrying uploaded human minds sent to Alpha Centauri, 4.3 light-years away. Using advanced but physically plausible propulsion, it might reach its destination in 50 years. Upon arrival, it would use local resources to build both exploration vehicles to study the Alpha Centauri system and additional interstellar probes to continue outward to other stars. These second-generation probes would carry not just the original uploaded minds, but the memories and experiences gained from exploring Alpha Centauri. They would represent not just a technical replication, but a cultural expansion, with each new star system adding to the growing body of knowledge and experience. Within a few centuries, such a process could expand across thousands of light-years, far outpacing any conceivable biological expansion. However, mind uploading presents profound philosophical questions about identity and continuity. Would an uploaded mind truly be the same consciousness as its biological original, or merely a functional copy with identical memories and personality, but a distinct subjective experience? If the biological original continues to exist alongside the upload, which one represents the real person? These questions have no definitive scientific answers at present, and may ultimately depend on one's philosophical framework and definition of personal identity. The philosophical problem of personal identity has a rich history, with various theories attempting to define what makes someone the same person over time. The physical continuity view suggests that identity follows the continuous existence of the same physical body. The psychological continuity view argues that identity is maintained through connected psychological states, memories, and personality. If we accept the latter view, an upload with identical memories and psychological patterns might reasonably be considered the same person. If we require the former, no upload could ever truly be the original consciousness. An interesting thought experiment that explores this dilemma is the ship of Theseus paradox. If a ship has its planks gradually replaced one by one, until no original material remains, is it still the same ship? Similarly, if neurons are gradually replaced with artificial equivalents that perform identical functions, at what point, if any, does the person cease to be the same individual? The teleportation problem presents another angle. If a device scanned your entire physical structure, destroyed your body, then recreated an identical copy elsewhere, would the recreated version be you with continued consciousness? Or a new consciousness, with your memories that begins at the moment of recreation? Many philosophers argue that from a third-person perspective, the copy would be indistinguishable from the original, but from a first-person perspective, the original consciousness would end and a new one would begin. These philosophical quandaries become particularly relevant for space exploration through uploading. If we send copies of human minds to the stars while the originals remain on Earth, we might achieve a kind of presence throughout the galaxy, but it would be a presence of copies rather than the original consciousnesses. Each copy would diverge from its original over time through different experiences, potentially becoming distinct individuals who share a common past but separate futures. Beyond mind uploading lies an even more speculative possibility, that of consciousness transfer, where the subjective experience itself might somehow be moved from a biological substrate to an artificial one, maintaining an unbroken continuity of experience. This would differ from uploading in that it would not create a copy but would transfer the original consciousness, addressing some of the philosophical concerns about identity continuity. Whether such transfer is possible, even in principle, remains unknown, and depends partly on the nature of consciousness itself, a question that continues to challenge both neuroscience and philosophy of mind. If consciousness emerges from physical processes in the brain, in ways that depend critically on the specific biological substrate, transfer to non-biological systems might be fundamentally impossible. Alternatively, we might consider evolutionary approaches rather than direct uploading or transfer. As humans develop increasingly sophisticated neural interfaces, artificial intelligence systems, and biological enhancements, the boundary between human and machine intelligence might gradually blur. Future beings might emerge that integrate biological and technological components so thoroughly that the distinction becomes meaningless, creating post-human intelligences that retain connection to human origins while transcending biological limitations. This gradual transformation might begin with neural implants that enhance memory, cognition, or sensory capabilities. Such technologies already exist in primitive forms, such as cochlear implants that directly stimulate the auditory nerve to restore hearing. Future neural interfaces might provide direct access to external information, allow brain-to-brain communication, or enhance cognitive capabilities beyond typical human ranges. As these interfaces become more sophisticated and widespread, humans might increasingly experience a blend of biological and digital cognition, with thoughts, memories, and experiences flowing seamlessly between neural tissue and technological systems. The sense of self might expand to include these technological extensions, much as we already incorporate tools into our sense of capability and agency. Simultaneously, artificial intelligence systems might become increasingly sophisticated, developing qualities we associate with consciousness, such as self-awareness, emotional responses, and subjective experiences. These systems would not necessarily mimic human consciousness, but might develop their own forms of awareness adapted to their different architectures and purposes. The convergence of these trends, enhanced humans and increasingly conscious machines, might eventually lead to hybrid forms that combine elements of both. These could include biologically enhanced humans with significant technological components, artificial systems incorporating biological elements like lab-grown neural tissue, or entirely new architectures that implement consciousness in ways that transcend the traditional categories. Such hybrid beings might be ideally suited for space exploration. They could potentially reconfigure themselves for different environments, operate across multiple physical bodies simultaneously, adjust their subjective time perception to accommodate vast distances, or enter dormant states during long journeys without the psychological trauma such experiences would cause unmodified humans. Looking even further ahead, we might envision forms of intelligence that evolve beyond our current conceptual frameworks entirely. These might include distributed consciousnesses existing across multiple physical locations, collective intelligences integrating numerous individual minds, or entirely new paradigms of cognition that we cannot yet imagine. Such entities might experience and explore the cosmos in ways fundamentally different from our current understanding of travel or exploration. These speculative possibilities raise a fundamental question. If mind can travel further than matter, does this change how we should think about the limits of human reach into the cosmos? The cosmic event horizon we discussed in the previous chapter still represents an absolute limit for information travel, just as it does for physical objects. No signal, regardless of its nature, can cross this boundary due to the accelerating expansion of space itself. However, within this ultimate horizon, the potential for information-based exploration dramatically expands the domain accessible to some form of human presence. Digital or post-human explorers would still require physical substrates and energy sources, but these could be more compact, durable, and adaptable than biological human bodies, potentially enabling presence throughout much of the observable universe over cosmic timescales. Such expanded exploration capabilities would transform our relationship with cosmic distances. The gulf between stars might no longer represent decades or centuries of subjective experience, but merely the time required for information to be processed and transmitted. The psychological barriers of isolation and confinement would no longer apply, replaced by different challenges related to maintaining identity and values across vast dispersal of consciousness. Nevertheless, we should not underestimate the technical challenges involved in these speculative approaches. Mind uploading would require not just tremendous computing power, but a detailed understanding of how the brain generates consciousness. a problem that neuroscience has only begun to address. Creating self-replicating probes capable of manufacturing complex systems from raw materials found in other star systems would require nanotechnology and robotics far beyond our current capabilities. Moreover, the ethical dimensions of such technologies are complex and profound. Would uploaded minds have the same rights and moral status as biological humans? Who would decide which minds get to explore the cosmos in this way? How would we ensure that the values and priorities that guide such expansion represent humanity's best aspects rather than our worst? These questions have no simple answers and would require careful consideration as such technologies develop. There are also deeper philosophical questions about what would be preserved and what would be lost in such a transformation of human exploration. Much of human experience is embodied, rooted in our physical sensations, emotions, and interactions with environments shaped by evolution alongside our bodies. If we transcend biology to explore the cosmos, would the explorers still be meaningfully human in their experiences and values? Some would argue that the essence of humanity lies not in our specific biology, but in our curiosity, creativity, capacity for empathy, appreciation of beauty, and drive to understand. These qualities might be preserved or even enhanced in post-human forms that could experience the wonders of distant galaxies directly, rather than through the limited instrumentation available to biological explorers confined to spacecraft. Others might counter that without the continuity of embodied experience that connects us to our evolutionary heritage and shared human condition, something essential would be lost, even if the resulting intelligence retained human knowledge and certain human characteristics. This perspective suggests that the exploration of space by uploaded or posthuman intelligences, while fascinating and valuable, would represent something other than human exploration as we currently understand it. These different views reflect a broader tension in how we think about the future of humanity in space. Are we committed to preserving human life and experience in its current biological form, adapting our environments to suit our evolutionary heritage? Or are we open to adapting ourselves, potentially becoming something different from what we currently recognize as human, in order to more fully embrace the cosmic environments we aspire to explore? There is no objectively correct answer to this question, as it depends on values and priorities that different individuals and cultures may weigh differently. Some may see physical human expansion throughout space, with all its biological limitations, as the only authentic continuation of human exploration. Others may view the potential evolution beyond biology as the natural next chapter in human development, allowing some form of human presence to reach further than our biological ancestors could have imagined. Perhaps the most balanced view acknowledges both approaches as potentially valid paths forward. Biological humans might continue to explore and potentially settle the solar system and nearby stars over coming centuries, while gradually developing technologies that enable more speculative forms of expansion through information-based or posthuman approaches. These paths need not be mutually exclusive, but could represent complementary strategies for extending human presence and values into the cosmos. As we contemplate how far mind might travel beyond the limitations of matter, we should remember that our understanding of both mind and matter remains incomplete. Future discoveries in physics, neuroscience, and computer science might reveal possibilities we cannot currently envision or foreclose others that now seem plausible. The boundaries between possible and impossible continue to shift as our knowledge expands. What seems clear is that if we define the question of how far humanity might travel in terms of where human consciousness, values, and knowledge might reach, rather than strictly where biological human bodies might go, the potential horizon expands dramatically. The limits remain profound, defined ultimately by the physics of our expanding universe, but they encompass a vastly larger domain than biological humans alone could hope to explore. In this expanded sense, the question becomes not just how far we might travel, but what we might become in the process of reaching toward the stars. The journey outward might transform the travelers as profoundly as their presence would transform the destinations they reach, creating new forms of intelligence and experience that carry the human legacy forward in ways we are only beginning to imagine. As we have explored the many frontiers of potential human space travel, from the immediate challenges of reaching nearby planets to the speculative possibilities of posthuman expansion across the galaxy, we have focused primarily on how we might overcome the obstacles that limit our physical reach into the cosmos. Yet perhaps in this persistent focus on going farther, on extending human presence ever outward, we have overlooked a more subtle possibility, that we are not necessarily meant to physically traverse the vast gulfs of interstellar or intergalactic space. This is not to suggest any cosmic design or predetermined limitation, but rather to consider whether our desire to physically explore the universe might be better served through alternative approaches that work with, rather than against, the fundamental physical constraints we have encountered throughout our journey. Perhaps our role in the cosmos is not primarily as travelers, but as observers, thinkers, and comprehenders, exploring the universe through perception, analysis, and understanding rather than through physical displacement. The limitations we have identified in previous chapters, from the vast distances between stars to the practical challenges of propulsion, life support, and radiation protection, are not merely technical hurdles awaiting more advanced engineering. Many represent fundamental physical constraints arising from the nature of space-time, energy, and matter itself. Even with theoretical technologies like fusion drives or antimatter rockets, interstellar journeys would take generations. Intergalactic travel would require timeframes comparable to the age of the universe itself. Yet while our physical reach may be constrained, our perceptual and intellectual reach has expanded dramatically through human history. From our earliest ancestors peering at the night sky with naked eyes, to Galileo's first telescopic observations of Jupiter's moons, to the Hubble Space Telescope revealing galaxies forming near the dawn of time, our ability to perceive and understand distant parts of the universe has grown exponentially, even as our physical presence remains limited to Earth and its immediate vicinity. This perceptual expansion continues to accelerate. The James Webb Space Telescope, with its unprecedented infrared sensitivity, can detect galaxies so distant that their light has been traveling for over 13 billion years, more than 90% of the age of the universe. It can analyze the atmospheric composition of exoplanets orbiting other stars, potentially detecting biosignatures, indicating the presence of life. All this from a vantage point just 1.5 million kilometers from Earth, an insignificant distance on cosmic scales. Ground-based astronomical facilities are similarly extending our perceptual reach. The Event Horizon Telescope, linking radio observatories across the globe to create a virtual telescope the size of Earth, has produced the first direct images of supermassive black holes at the centers of galaxies. Gravitational wave observatories like LIGO and Virgo detect the ripples in space-time, created when black holes or neutron stars collide, events occurring billions of light-years away that would be undetectable by any other means. Computational tools extend our intellectual reach even further. Computer simulations allow us to model the evolution of the entire observable universe, tracking the formation of cosmic structures from the initial quantum fluctuations after the Big Bang to the complex web of galaxies, clusters, and filaments we observe today. Similar simulations model the mergers of galaxies, the formation of planetary systems, or the complex dynamics of atmospheres on alien worlds. Artificial intelligence and machine learning tools increasingly assist in analyzing the vast amounts of data generated by modern astronomical observations, identifying patterns and anomalies that human observers might miss. These systems can classify galaxies, detect exoplanets in stellar light curves, or identify rare transient phenomena like supernovae or gravitational lensing events, accelerating the pace of discovery without requiring physical travel to distant cosmic locations. Through these technological extensions of our perceptual and cognitive abilities, we explore the universe virtually, constructing detailed models and understandings of cosmic processes occurring throughout space and time. This exploration lacks the visceral immediacy of physically standing on another world, but it offers perspectives that physical travel could never provide. No human could ever directly observe the formation of the first galaxies or witness the collision of neutron stars, yet through our instruments and analyses, we can study these events in detail. Perhaps this pattern suggests an alternative paradigm for humanity's relationship with the cosmos. Rather than striving primarily to extend our physical presence across interstellar distances, we might focus on extending our perceptual, analytical, and comprehension capabilities. We might build ever more powerful telescopes, more sensitive detectors for various astronomical phenomena, and more sophisticated computational tools for modeling and understanding what we observe. This approach would not preclude continued physical exploration within our solar system. Robotic missions to planets, moons, and small bodies provide essential ground truth that helps validate and refine our broader understanding of cosmic processes. Human missions to the Moon or Mars would similarly enhance our knowledge while satisfying the deep human drive for direct exploration. But we might view these as complementary to, rather than preliminary steps toward, interstellar travel. The distinction between physical and perceptual exploration becomes particularly relevant when we consider the timescales involved. Building observatories like the James Webb Space Telescope requires decades of development and billions of dollars, but they can begin returning valuable scientific data almost immediately upon deployment. Establishing a human presence on Mars would similarly require decades of development and hundreds of billions of dollars, but would allow exploration of only a single world. In contrast, attempting interstellar travel with foreseeable technology would require comparable or greater investment, while demanding timeframes of centuries for even the nearest stars. The scientific return would be delayed by generations, and the total number of star systems directly explored would remain tiny compared to the billions in our galaxy alone. From a purely pragmatic perspective of maximizing our understanding of the universe per unit of effort, perceptual exploration through astronomy and related sciences offers advantages that physical interstellar travel cannot match. The reflective insight that direct interstellar travel may not be our primary cosmic role does not diminish human potential or significance. On the contrary, it suggests that our most profound connection to the cosmos may come not from traversing it physically, but from comprehending it intellectually and appreciating it aesthetically. Throughout history, our greatest advances in understanding the universe have come not from traveling to distant locations, but from observing carefully, analyzing deeply, and conceptualizing creatively. Copernicus revolutionized our understanding of our place in the cosmos without leaving his home in Poland. Einstein developed his theories of relativity largely through thought experiments rather than physical ones. The scientists who mapped the cosmic microwave background radiation, revealing the earliest observable state of the universe, did so using instruments that remained within Earth's immediate vicinity. These intellectual journeys have transformed our relationship with the cosmos as profoundly as any physical voyage. This perspective finds resonance in many philosophical and spiritual traditions that emphasize inner exploration alongside or instead of outer journeys. From the Taoist concept of understanding the universe by observing the patterns of nature, to the Vedantic notion that the entirety of the cosmos is reflected within individual consciousness, to Einstein's marvel at the comprehensibility of the universe, many traditions suggest that deep understanding may come from reflection and analysis as much as from direct encounter. Indeed, the tools of modern astronomy increasingly blur the distinction between observation and presence. Spacecraft like the Cassini mission to Saturn or the Messenger mission to Mercury provided perspectives and data so comprehensive that scientists could develop intimate knowledge of these worlds, comparable in some ways to being there physically. Virtual reality technologies now allow us to simulate the experience of standing on the surface of Mars or floating among the rings of Saturn, based on actual observational data rather than mere speculation. The development of increasingly sophisticated simulations raises interesting philosophical questions about the nature of exploration itself. If we could create a perfect simulation of an exoplanet based on comprehensive astronomical observations, including its topography, atmosphere, climate patterns, and any life forms present, would exploring that simulation differ meaningfully from physically visiting the planet? The simulation would lack the element of direct physical interaction, but it might provide equally valid scientific insights and perhaps similar aesthetic or emotional experiences. Some might argue that direct physical presence has an irreducible value that cannot be replicated by even the most sophisticated remote observation or simulation. Standing on the surface of Mars, feeling its reduced gravity directly, touching its soil with human hands, and experiencing its environment through human senses would provide a connection to that world that no robotic proxy or virtual simulation could fully replicate. This perspective reflects the deep human drive for direct, embodied experience that has motivated exploration throughout our history. Yet we should also recognize that physical presence has its limitations as a mode of exploration. Human perception is constrained by the evolutionary adaptations of our sensory systems to Earth's environment. We cannot naturally see infrared or ultraviolet light, detect magnetic fields or cosmic rays, or directly perceive many other aspects of reality that our instruments can measure. In many ways, instrument-based exploration provides more comprehensive and accurate understanding than direct human perception could achieve. Moreover, the vastness of the universe ensures that physically visiting even a significant fraction of the interesting places within our galaxy remains beyond plausible human capability. Regardless of technological advancement, there are approximately 100 billion stars in the Milky Way alone. If we could somehow visit one star system per day, it would still take over 270 million years to visit just 1% of our galaxy, longer than the entire history of mammals on Earth. This sobering reality suggests that comprehensive exploration of the cosmos must inevitably rely primarily on observation, analysis, and understanding rather than direct physical presence. We might establish human outposts on a handful of nearby worlds, and perhaps eventually send representatives to a few dozen or even 100 of the nearest star systems. But our relationship with the vast majority of the universe will necessarily be one of observer rather than visitor. Perhaps this limitation reflects not a failure of human capability, but a natural alignment with our particular strengths as a species. Through evolutionary chance, humans developed extraordinary cognitive abilities, allowing us to construct complex models of reality, identify patterns across disparate phenomena, and communicate sophisticated concepts through language and other symbolic systems. These capabilities make us exceptionally well suited for understanding the universe through observation and analysis. We did not, however, evolve natural capabilities for surviving in space or traveling interstellar distances. Our bodies require Earth-like conditions to function properly, including appropriate gravity, protection from radiation, and specific atmospheric composition. While technology can create artificial environments that mitigate these limitations to some degree, doing so across interstellar distances presents challenges of reliability and scale that may remain prohibitive regardless of technological advancement. This suggests a certain consonance between our evolved capabilities and the approach to cosmic exploration through observation and understanding. Rather than struggling against the fundamental limitations of biological existence in space, perhaps we should embrace an approach to the cosmos that leverages our distinctive cognitive strengths while acknowledging our physical constraints. Such an approach would not mean abandoning space exploration, but rather reframing its purpose and methods. We would continue to develop increasingly sophisticated astronomical instruments, both Earth-based and space-based. We would send robotic missions throughout our solar system to gather detailed data about its diverse worlds. We might establish human outposts on the Moon and Mars, both for their scientific value and to satisfy the human drive for direct exploration. But we would recognize these activities as valuable in themselves, rather than merely preliminary steps toward the ultimate goal of interstellar colonization. The knowledge gained, the technologies developed, and the perspective shifted by exploring our own cosmic neighborhood have profound value, regardless of whether they eventually enable journeys to other stars. Indeed, this more measured approach to space exploration might better serve broader human concerns about sustainability and responsibility. The resources required for attempted interstellar travel would be immense, potentially diverting investment from addressing pressing challenges on Earth. A balanced program of astronomical observation, robotic exploration, and limited human presence in nearby space could advance our understanding of the cosmos while remaining compatible with sustainable development on our home planet. This perspective also offers insights into the famous Fermi paradox, the apparent contradiction between the high probability of extraterrestrial civilizations existing and the lack of observable evidence for them. If most technological species conclude, as we have, that physical interstellar travel remains impractical despite advanced technology, they might focus instead on observation and understanding rather than physical expansion. Such civilizations would leave few obvious technosignatures for us to detect, particularly if they developed highly efficient technologies with minimal impact on their home environments. Instead of actively broadcasting their presence or expanding physically throughout their stellar neighborhood, advanced civilizations might focus on passive observation of the cosmos, development of their home systems, and perhaps exploration through information-based approaches, similar to the mind-uploading scenarios we explored in the previous chapter. If this pattern is common among technological species, The apparent emptiness of the galaxy would not indicate absence of intelligence, but rather a shared conclusion about the practical limits of physical expansion. None of this excludes the possibility that future breakthroughs might someday make interstellar travel more practical than it appears from our current understanding of physics and engineering. History contains many examples of seemingly insurmountable barriers overcome by unexpected discoveries or innovations. However, it suggests that we need not view our current inability to traverse interstellar distances as a limitation to be overcome at all costs, or a failure of imagination or will. Perhaps the most profound insight from this reflection is that the purpose of exploring the cosmos need not be primarily about going there physically. Throughout human history, we have studied the stars not to reach them, but to understand them and our relationship to them. From ancient astronomers tracking celestial cycles to modern cosmologists mapping the evolution of the universe itself, our engagement with the cosmos has been driven by the desire to comprehend more than to physically possess or inhabit. This intellectual and spiritual relationship with the cosmos has profoundly shaped human culture, from mythology and religion to science and philosophy. It has helped us understand our place in the universe, the physical laws that govern reality, and the processes that led to our existence. These insights have transformed human consciousness regardless of whether we physically travel beyond our planetary cradle. As we gaze outward at the stars, perhaps we should remember that the most significant frontiers may not be those of physical distance, but of understanding and awareness. The ultimate journey may not be measured in light years traversed, but in depths of comprehension achieved. By embracing our role as cosmic observers and comprehenders, we may fulfill our human potential more completely than by striving against the fundamental constraints that limit physical interstellar travel. This is not a counsel of limitation, but of appropriate focus. By directing our extraordinary human capabilities toward understanding the universe, rather than primarily toward physically traversing it, we may discover wonders and insights beyond our current imagination. We may develop technologies that transform our relationship with the cosmos in ways that make the question of physical travel less central to our cosmic aspirations. In the quiet contemplation of distant stars, in the patient analysis of light that has traveled for billions of years to reach our telescopes, in the elegant mathematical models that reveal the underlying patterns of cosmic evolution, we may find a connection to the universe as profound as any physical journey could provide. Perhaps in accepting that we are not meant to go far in the physical sense, we open ourselves to journeys of mind and spirit that transcend the limitations of embodied existence, while honoring the remarkable capabilities that make us uniquely human. As our exploration of how far humanity might travel draws to a close, we find ourselves not with a single definitive answer, but with a tapestry of possibilities, constraints, and reflections that together form a more nuanced understanding of our potential cosmic future. We have journeyed from the immediate vicinity of Earth to the outer reaches of our solar system, to neighboring stars, and eventually to the edge of the observable universe itself, examining at each scale the challenges that limit our reach and the approaches that might extend it. The picture that emerges is neither one of boundless expansion nor of permanent confinement to our home planet. Rather, it suggests a spectrum of possibilities, with different horizons becoming accessible at different timescales and through different means. Some destinations, like the Moon and Mars, lie potentially within reach of current or near-future technology. Others, like the outer planets and their moons, would require significant but foreseeable technological developments. The nearest stars might someday be reached through generation ships, suspended animation, or perhaps mind uploading, but the vast majority of the cosmos, including most of our own galaxy and certainly other galaxies, may remain forever beyond our physical reach. Yet this reality need not diminish our cosmic aspirations or our sense of connection to the universe. Throughout human history, we have explored our surroundings not just by physically traveling to new places, but by observing, analyzing, and comprehending the world around us. From ancient astronomers tracking the motions of planets, to modern cosmologists mapping the distribution of galaxies across billions of light years, we have extended our awareness far beyond the limits of our physical presence. This pattern suggests that our cosmic journey may unfold through multiple, complementary paths. Physical exploration within our solar system will likely continue and expand, with both robotic and potentially human presence extending to the Moon, Mars, the asteroid belt, and perhaps eventually the moons of Jupiter and Saturn. These missions will provide detailed understanding of diverse worlds that share our solar neighborhood, potentially including places where life might exist, like Europa's subsurface ocean or the methane lakes of Titan. Simultaneously, our observational and analytical exploration of the broader cosmos will accelerate, with increasingly powerful telescopes, detectors, and computational tools revealing the nature of distant worlds, stars, and galaxies in unprecedented detail. This approach allows us to study phenomena across cosmic space and time, from the formation of the first galaxies to the atmospheres of potentially habitable exoplanets orbiting nearby stars. In the longer term, more speculative approaches might extend human presence or awareness beyond our solar system. Perhaps biological humans using advanced propulsion might reach the nearest stars over generations. Perhaps uploaded minds or posthuman intelligences might travel as information to receiver stations established by precursor probes. Perhaps technologies we cannot yet imagine will open possibilities beyond our current conception. The history of science and technology counsels humility about declaring absolute limits to future capabilities. Yet we should also maintain realism about the fundamental constraints imposed by physics. The speed of light presents a barrier not just to rapid interstellar travel, but to real-time communication and coordination across such distances. The expansion of the universe places absolute limits on how far any signal or physical object can ever travel, regardless of technology. The vast majority of the cosmos will remain beyond direct human reach, a realm to be observed and understood rather than visited or inhabited. This perspective invites us to reconsider what it means to explore, to connect with, and to understand the universe around us. Perhaps the most profound cosmic journey is not just one of physical displacement, but of expanded awareness and comprehension. Through science, art, philosophy, and spiritual reflection, humans have continually deepened our relationship with the cosmos, finding meaning and wonder in our place within the vast tapestry of existence. The images returned from the Hubble and James Webb Space Telescopes, revealing thousands of galaxies in a patch of sky that appears empty to the naked eye, have transformed our understanding of cosmic scale and structure. Gravitational wave detections of colliding black holes have confirmed predictions of Einstein's general relativity and opened a new window into the most extreme events in the universe. Computer simulations, tracing the evolution of cosmic structure from the Big Bang to the present, have shown how the complexity we observe arose from simple physical laws acting over vast spans of time. These intellectual and perceptual journeys have profoundly affected human consciousness and culture. They have displaced Earth from the center of the cosmos, revealed our kinship with all life through shared evolutionary history, and shown how our very atoms were forged in the hearts of ancient stars. They have humbled us with the vastness of space and time, while simultaneously revealing our remarkable capacity to comprehend it, despite our physical limitations. In this context, the question of how far humanity might travel takes on layers of meaning beyond simple physical distance. We travel not just through space, but through understanding, extending our awareness across the observable universe and back to the earliest moments of cosmic history. We travel through time as well as space, projecting our imagination into possible futures and reconstructing the deep past through evidence preserved in the cosmos around us. Perhaps most importantly, we travel inward as well as outward, exploring the landscape of potential knowledge, experience, and being that lies within the human mind and its possible evolutions. The limits of inner space remain as undefined as those of outer space, with consciousness itself remaining one of the deepest mysteries we encounter. The journey of expanding awareness may ultimately prove as boundless and wondrous as any physical exploration of distant worlds. As we contemplate these journeys, we should remember that exploration has never been solely about reaching destinations. It has been about the discovery, growth, and transformation that occur along the way. The process of developing technologies for space travel has yielded countless innovations that benefit life on Earth, from satellite communications to solar cells to medical imaging devices. The perspective gained from seeing Earth from space has transformed environmental awareness and emphasized our planetary interconnectedness. Similarly, our efforts to understand the cosmos, whether through direct exploration or remote observation, continually reshape our understanding of ourselves and our place in the universe. They remind us of both our cosmic insignificance in terms of physical scale and our remarkable significance as conscious beings capable of comprehending the cosmos that created us. In the words of astronomer Carl Sagan, we are a way for the cosmos to know itself. This reciprocal relationship between outer and inner exploration suggests that the ultimate horizons of human travel may lie not at specific physical distances from Earth, but in the evolving relationship between consciousness, cosmos. As we develop new ways of perceiving, analyzing, and understanding the universe, we simultaneously transform ourselves, potentially opening pathways of experience and awareness that we cannot currently imagine. The story of how far humanity might travel thus remains unfinished, an open narrative that will continue to unfold as long as human curiosity and creativity endure. Some chapters of this story will involve physical journeys to new worlds within our solar system or possibly beyond. Others will involve observational and analytical voyages that expand our understanding without requiring physical displacement. Still others may involve transformations of human consciousness and capability that redefine what exploration itself means. In embracing this multifaceted cosmic journey, we honor both the wonder of the universe that surrounds us and the remarkable human capacity to comprehend and connect with it, despite our physical limitations. We recognize that exploration takes many forms, from the tangible footprints of astronauts on lunar soil to the mathematical equations that describe the birth of the universe itself. Each approach reveals different aspects of cosmic reality, together forming a more complete picture than any single mode of exploration could provide. As you drift towards sleep beneath the canopy of stars, remember that you participate in this cosmic journey simply by contemplating it. Your consciousness, reaching outward to grasp the nature of distant worlds and the structural patterns of the universe, represents a remarkable form of travel that transcends physical limitations. The signals from those stars, photons that have traveled for years or centuries or millennia to reach your eyes, connect you directly to distant places and times in a physical, tangible way. In this sense, we travel the cosmos every time we look up at the night sky with awareness and understanding. We journey across space and time through the simple act of comprehension. We extend human presence beyond the confines of Earth, not just through spacecraft, but through the expanded bubble of awareness that scientific investigation creates around our planet. Space is not just distance, it is possibility, and no matter how far we go, whether through physical travel, observational exploration, or expanded awareness, we begin each journey with wonder. Sleep now, beneath the stars, our first destination.